The Banach-Tarski paradox is one of the most fascinating and counterintuitive results in modern mathematics, revealing that a solid sphere in three-dimensional space can be divided into a finite number of disjoint pieces and then reassembled using only rotations and translations into two spheres identical to the original. This astonishing outcome challenges our conventional understanding of volume and conservation because it appears impossible for one object to be perfectly duplicated merely by cutting it into parts and rearranging them without any addition of new material. The paradox fundamentally relies on the axiom of choice, a powerful yet sometimes controversial principle in set theory. This axiom allows the selection of elements from an infinite collection of sets in a non-constructive way, enabling the construction of sets that are so wild or pathological that they defy our usual notions of measurable volume. Consequently, the pieces created in the Banach-Tarski construction have no well-defined size, and the standard arithmetic of volume does not apply. Although the idea that one sphere can be reassembled into two identical copies seems to violate conservation laws observed in everyday objects, it is important to understand that the paradox exists solely within the realm of pure mathematics. No actual physical sphere can be manipulated in the same way because the pieces produced are highly non-measurable and cannot be realized by any physical process. Thus, the paradox highlights a stark distinction between mathematical abstraction and physical reality. The proof of the Banach-Tarski paradox involves advanced concepts from group theory and measure theory, particularly the use of free groups, and the discovery that the rotation group in 3 dimensions contains subgroups isomorphic to free groups on 2 generators. These groups exhibit properties that lead to paradoxical decompositions. It is precisely the non-amenable nature of these groups that makes such a decomposition possible in 3 or more dimensions, while in 1 or 2 dimensions, the necessary conditions fail. This result underscores the limitations of our intuitive ideas about space and volume and emphasizes the profound implications of accepting the axiom of choice as a foundational component of modern set theory. Many mathematicians have expressed discomfort with this axiom because it enables phenomena like the Banach-Tarski paradox, even though it is indispensable in numerous other areas of mathematics where its consequences are both natural and desirable. Over the years, the paradox has spurred extensive debate among mathematicians and philosophers, prompting discussions about the nature of infinity, the relationship between physical reality and abstract mathematical theory, and the significance of precise definitions in mathematics. By demonstrating that familiar notions of size and volume can break down under certain abstract conditions, the Banach-Tarski paradox serves as a powerful example of how advanced mathematical reasoning can lead to results that defy common sense, while remaining logically consistent. Ultimately, the Banach-Tarski paradox stands as a testament to the creative and sometimes bewildering consequences of abstract mathematical thought. It invites us to re-examine our intuitive perceptions of space and to appreciate the surprising depths that lie within even the simplest geometric objects when viewed through the lens of modern set theory and algebraic techniques. The Coastline Paradox is a fascinating phenomenon that challenges the intuitive notion of length by showing that the measured length of a coastline can vary dramatically depending on the size of the measuring tool used. When you measure a smooth, simple shape like a straight line, the length remains constant regardless of the scale of measurement. However, coastlines are notoriously irregular. full of twists, turns, and intricate details that become more pronounced the closer you look. If you use a long ruler, you capture only the broad strokes of the coastline, missing many of its indentations and inlets. But as you switch to a shorter ruler, you begin to trace every small cove and bay, resulting in a longer overall measurement. This paradox was first observed by the mathematician Lewis Fry Richardson, who noticed that the measured length of national coastlines depended on the scale of the map used. Later, Benoit Mandelbrot's work in fractal geometry provided a theoretical foundation for understanding why this occurs. Mandelbrot showed that many natural objects, including coastlines, have fractal-like properties, a complex structure that repeats itself at different scales. This means that no matter how much you zoom in, you continue to find more detail, and consequently, more length. The key idea behind the Coastline Paradox is that the concept of length becomes ambiguous when applied to jagged, natural formations. Imagine trying to measure the edge of a rugged cliff with a piece of string. If the string is long, it will bridge over many small crevices and irregularities, giving you a shorter measurement. However, if the string is very short, you can follow the intricate path of the edge much more precisely, leading to a longer total length. In theory, as the measuring unit approaches an infinitely small scale, the measured length can approach infinity, because the string can zigzag its way into every minor nook and cranny. What makes this idea even more intriguing is its connection to the concept of fractals. Fractals are geometrical objects that display self-similarity across different scales, meaning that a small section of a fractal looks similar to the whole. While natural coastlines aren't perfect fractals, they often exhibit fractal-like properties. This self-similarity contributes to the difficulty in defining a true length for a coastline, because the detail you observe depends entirely on how finely you are examining the edge. A classic example, often cited, is the coastline of Great Britain, which has been measured in numerous ways to yield vastly different results. Early measurements estimated its length to be only a few hundred miles, while later, more detailed studies have resulted in figures that are many times larger. This discrepancy is not due to errors in measurement, but is a natural consequence of the coastline's inherent complexity. As one refines the measurement process with smaller and smaller units, the calculated length increases, illustrating that the coastline's true length is not fixed, but is scale-dependent. In practical terms, the Coastline Paradox has significant implications for geography, cartography, and even environmental science. It forces scientists to reconsider how they measure irregular shapes and to accept that some natural features may defy conventional geometric definitions. Rather than seeking a single, definitive measure, researchers have adopted concepts from fractal geometry to describe the complexity of coastlines. This has led to a more nuanced understanding of natural systems, highlighting the interplay between scale and detail. Ultimately, the Coastline Paradox serves as a compelling reminder that the measurements we take for granted in everyday life can become problematic when applied to the natural world. It challenges the classical idea that objects have fixed properties, showing instead that measurements can be relative and dependent on the method employed. Far from being a mere mathematical curiosity, this paradox has opened up new avenues for exploring the complexity of nature. It underscores the limitations of traditional Euclidean geometry when faced with the rugged, intricate patterns found in the real world. In essence, the Coastline Paradox is a beautiful example of how mathematics can reveal unexpected insights about the natural environment. It prompts us to think more deeply about the concepts of measurement and scale, and how these ideas apply to objects that do not conform to our simplified models. By exploring this paradox, we gain a greater appreciation for the underlying patterns and structures that define our world, even in the seemingly chaotic edges of a winding shoreline. The Monty Hall problem is a classic puzzle in probability that challenges our intuition and reveals how our initial judgments about chance can be misleading. Imagine you're on a game show with 3 doors. Behind one door is a shiny car, and behind the other 2 are goats. At the start, you choose one door. Naturally, you have a 1 in 3 chance of having picked the car, and a 2 in 3 chance that the car is behind one of the other 2 doors. After your choice, the host, who knows what lies behind each door, opens one of the remaining doors to reveal a goat. Now, you are given a choice. Stick with your original door or switch to the other unopened door. The twist is that switching your choice actually doubles your chance of winning the car. When you first picked a door, the odds were 1/3 for the car and 2/3 for a goat, and these probabilities do not change just because a door is opened. The host's action is not random. He intentionally reveals a goat, and this extra piece of information influences the outcome. By opening a door with a goat, the host effectively transfers the 2/3 probability from the 2 unchosen doors to the 1 remaining unopened door. Consequently, if you switch, your chance of winning the car increases to 2/3, while sticking with your original choice leaves you with only a 1/3 chance. Many people find this result hard to believe because it conflicts with the notion that, once one door is eliminated, the remaining 2 doors would each have equal probabilities of 50%. However, the key lies in understanding that the host's intervention is based on his knowledge of what's behind the doors. His decision to open a door that he knows hides a goat isn't random. It's a deliberate move that alters the initial probability distribution. The fact that your initial choice remains at 1/3 probability, while the chance that the car is behind one of the other doors collectively stays at 2/3, is the crux of the puzzle. To put it in another perspective, imagine that instead of 3 doors, there were 100 doors. You pick one door, and then the host, knowing where the car is, opens 98 doors, each revealing a goat. In that case, your chosen door still has a 1 in 100 chance of containing the car, while the remaining unopened door now carries a 99 in 100 chance. Such an example makes it clearer why switching is the better strategy. With so many doors, it becomes apparent that your original choice was highly unlikely to be correct. The Monty Hall problem serves as a powerful lesson in conditional probability and decision theory. It shows that when new information is introduced, in this case, the host revealing a goat, the probabilities can shift in ways that are not immediately obvious. This phenomenon has been rigorously analyzed with mathematical proofs and supported by computer simulations and experiments, all consistently confirming that switching is the optimal strategy. What makes this problem so captivating is not just the result itself, but also the way it exposes the pitfalls of our intuition. It reminds us that our gut feelings about fairness and chance can sometimes lead us astray, particularly when we deal with situations that involve complex conditional probabilities. Many contestants on actual game shows may feel uneasy about switching their choice, clinging to the instinct that their initial intuition must be correct, even when logic and probability suggest otherwise. In broader terms, the Monty Hall problem illuminates the sometimes counterintuitive nature of probability theory and encourages us to re-examine how we perceive risk and reward. It's a great example of why statistical thinking is essential, not only in games, but also in real-life situations where decisions must be made under uncertainty. By embracing a more analytical approach and understanding the underlying mechanics of probability, we can often come to more informed and beneficial decisions. Ultimately, the Monty Hall problem isn't just about doors, goats, and a car. It's a metaphor for the unexpected ways that information and strategy can intersect. It challenges us to question our assumptions and to be open to revising our strategies when new evidence comes to light. Whether you're a student of mathematics, a fan of game shows, or simply someone interested in the quirks of logical reasoning, the puzzle offers a brilliant demonstration of how rigorous analysis can reveal truths that defy our everyday expectations. So, the next time you face a decision that involves uncertain outcomes, remember the lesson of the Monty Hall problem. Sometimes, switching your approach can significantly boost your odds of success, even if it seems to go against your initial intuition. Hilbert's Grand Hotel is a remarkable thought experiment that vividly illustrates the bizarre yet fascinating properties of infinite sets in mathematics. It begins with a hotel that has an infinite number of rooms, each uniquely numbered 1, 2, 3, and so forth, extending indefinitely. Despite every single room being occupied, the hotel is never truly full in the conventional sense, because the set of natural numbers, which represents the room numbers, is infinite. This simple idea challenges our everyday experience with finite sets, where occupancy equals capacity, and shows that with infinity, our usual rules no longer apply. Imagine that every room in this hotel is occupied when a new guest arrives. Intuition might suggest that no vacancy exists, but the manager of Hilbert's Grand Hotel has a clever strategy to create space. He simply instructs the guest in room 1 to move to room 2, the guest in room 2 to move to room 3, and so on. This one-room shift means that room 1 becomes available for the new guest. Although every guest still has a room, the infinite nature of the hotel allows for this seemingly paradoxical rearrangement without displacing anyone permanently. The real magic of Hilbert's Grand Hotel becomes even more striking when an infinite number of new guests arrive at the fully occupied hotel. Instead of a single shift, the manager employs a more dramatic strategy. He asks every current guest to move from room N to room 2N. This maneuver relocates every guest into an even-numbered room, leaving all the odd-numbered rooms completely empty. Since the odd numbers form an infinite subset of the natural numbers, there is now an infinite amount of vacant rooms available for the new arrivals. This counterintuitive scenario vividly demonstrates that the union of two infinite sets, such as the original guests and the new guests, can still be equivalent in size to the initial infinite set, a result that defies our finite intuitions. Hilbert's Grand Hotel is more than just a clever puzzle. It highlights the principle of one-to-one correspondence in set theory. In finite sets, matching every element of one set to another ensures that the sets are of equal size. With infinite sets, however, it is possible to establish such one-to-one correspondences even when new elements are added or when the set is rearranged. This property is fundamental to understanding the concept of cardinality in mathematics. For countably infinite sets, like the natural numbers, adding or even pairing with another countably infinite set does not change the overall size of the set. This is a powerful and somewhat non-intuitive idea that has profound implications not only in mathematics, but also in philosophy, computer science, and other disciplines that deal with the infinite. Exploring Hilbert's Grand Hotel leads to interesting reflections on the nature of infinity itself. In our everyday world, the idea that something can be filled to capacity and still have room for more seems absurd. Yet in the realm of infinite sets, the rules are different. Infinity is not a number you can count to. Rather, it is a concept that requires its own unique set of properties and operations. This thought experiment not only clarifies the concept of infinity, but also forces us to re-examine how we measure and understand the size of sets that extend beyond our finite experiences. The implications of Hilbert's Grand Hotel extend well beyond a quirky mathematical idea. It challenges the very notion of what fullness means when dealing with infinite quantities, and shows that infinite sets can be manipulated in ways that defy ordinary logic. This understanding is critical in advanced areas of mathematics, such as topology, analysis, and even in theoretical computer science, where dealing with infinite processes or data structures is a common challenge. Moreover, Hilbert's Grand Hotel provides a foundation for understanding more complex types of infinities, like uncountable infinity, where the rules become even more intricate and nuanced. Ultimately, Hilbert's Grand Hotel stands as a brilliant metaphor for the peculiar and wondrous world of infinity. It encourages us to let go of our finite intuitions and to embrace the abstract yet rigorously defined properties of infinite sets. In doing so, it not only deepens our understanding of mathematics, but also opens our minds to new possibilities, proving that even a hotel that seems full to the brim can always welcome more guests. Time dilation in relativity is one of the most striking ways mathematics reveals that moving faster can literally slow down time. The concept originates from Einstein's theory of special relativity, which fundamentally altered our understanding of space and time by showing that they are not separate, absolute entities, but rather interwoven aspects of a four-dimensional continuum. One of the key predictions of this theory is that a clock moving relative to an observer will tick more slowly compared to a clock at rest with respect to that observer. To understand this mathematically, consider the idea of a light clock, a simple device that measures time by reflecting a beam of light back and forth between two mirrors. If the clock is stationary relative to an observer, the light travels a straightforward up and down path. However, when the clock is moving at a high velocity, the path of the light beam, as seen by a stationary observer, becomes diagonal because the entire clock is moving forward during the time it takes for light to bounce between the mirrors. Since the speed of light is constant, the light must cover more distance with each tick in the moving clock compared to the stationary clock. This longer path implies a longer time between ticks, which is precisely what we call time dilation. The mathematics behind this phenomenon is encapsulated in what is known as the Lorentz transformation. Central to these transformations is the Lorentz factor, denoted by the Greek letter gamma, which is defined as gamma equals 1 over the square root of 1 minus v squared over c squared, where v represents the relative velocity of the moving object, and ECO is the speed of light in a vacuum. According to this formula, as the speed v approaches the speed of light, the factor gamma increases dramatically, meaning that the moving clock slows down significantly relative to a clock at rest. In practical terms, if a stationary observer measures a time interval, delta t, the corresponding time interval experienced by the moving observer, known as the proper time delta t0, will be shorter, with the relationship given by delta t equals gamma delta t0. This mathematical relationship has been confirmed in numerous experiments. One of the most famous is the observation of muon decay. Muons are subatomic particles created high in the Earth's atmosphere by cosmic rays. In their rest frame, muons decay very quickly and would not be expected to reach the surface of the Earth. However, because they are moving at speeds very close to the speed of light, time dilation means that the muons experience time more slowly than we do. As a result, many more muons reach the Earth's surface than classical physics would predict. Additionally, precise experiments using atomic clocks flown on airplanes and satellites have measured time differences in agreement with predictions from special relativity. These experiments confirm that our mathematical description of time dilation isn't merely an abstract idea, but a real effect that influences systems in our universe. The implications of this phenomenon are far-reaching. Not only does time dilation challenge our everyday experiences with time, but it also forces us to reconsider how we understand the flow of time itself. In the realm of high-speed travel, such as when imagining journeys close to the speed of light, this effect becomes significant. Travelers moving at these speeds would age more slowly compared to people remaining on Earth, a concept often referred to as the twin paradox, where one twin makes a high-speed journey while the other stays on Earth, and upon reunion, the traveling twin is noticeably younger. The counterintuitive nature of time dilation arises from our everyday encounters with slow speeds, where the effects are so minuscule that they go completely unnoticed. In our daily lives, the difference in the passage of time due to relative motion is negligible, but mathematically, the framework provided by the Lorentz transformations holds true regardless of the speed. This consistency across all speeds, not just the extremes, demonstrates the power of mathematics in unifying our understanding of physical phenomena. It shows that even concepts as seemingly fixed as time are subject to fundamental laws that can be described with elegant formulas. Another way to view time dilation is through the invariance of the space-time interval, a concept that unites time and space into a single fabric. The space-time interval between two events is given by s squared equals c squared delta t squared minus delta cx squared, and this quantity remains the same for all observers, regardless of their state of motion. When an observer is moving relative to another, the measurements of time, delta t, and space, delta x, adjust in such a way that the interval s remains constant. This invariance underpins the entire theory of special relativity and mathematically ensures that the faster one moves, the slower time passes relative to a stationary frame of reference. The beauty of this mathematical structure is that it not only predicts time dilation, but also provides insight into many other relativistic effects, such as length contraction and the relativity of simultaneity. All these effects are interconnected through the Lorentz transformations and highlight a universe where the fabric of space-time is flexible and dynamic, rather than rigid and absolute, as classical physics once suggested. Understanding time dilation has also practical applications. The precise timing provided by GPS satellites is adjusted for both the effects of their orbital speeds and the differences in gravitational potential compared to the surface of the Earth. Without correcting for time dilation, the GPS system would quickly become inaccurate, demonstrating that these mathematical principles are essential even in everyday technology. In summary, the mathematics of special relativity via the Lorentz factor and the invariance of the space-time interval compellingly shows that as an object moves faster, time itself slows down relative to an observer at rest. This idea challenges our intuitive understanding of time, illustrating that the passage of time is not an immutable constant, but a flexible quantity intertwined with space and motion. Through mathematical derivations and experimental validations such as muon decay and precision clock measurements, time dilation stands as one of the most powerful examples of how abstract mathematical concepts can unlock profound truths about the nature of our universe. The birthday paradox is a fascinating example of how our intuition about probability can be wildly off when it comes to understanding how chances accumulate. Imagine walking into a room where there are 23 people. Most of us would assume that with 365 possible birthdays, the odds of any two individuals sharing the same birthday are very slim. After all, 23 is such a small fraction of 365. However, when you actually crunch the numbers, you find that there's about a 50% chance that at least two people in that group share the same birthday. The key to understanding this paradox lies in the idea that it's not just the individual's birthdays that matter, it's all the possible pairs that can be formed within the group. In a room with 23 people, there are a total of 253 distinct pairs of individuals. Even though the chance that one particular pair shares a birthday is low, about 1 in 365, the fact that there are so many pairs makes it much more likely that somewhere among those 253 pairs, two people will have the same birthday. To delve into the math behind it, consider calculating the probability that no two people in the room share a birthday. For the first person, there's no restriction. They can be born on any of the 365 days. For the second person to avoid sharing a birthday with the first, there are 364 days left, giving a probability of 364 over 365. For the third person, who must avoid matching the birthdays of the first two, the probability is 363 over 365, and this pattern continues. Multiplying these probabilities together for all 23 people gives the probability that everyone has unique birthdays. When you compute this product, the chance of no shared birthdays turns out to be less than 50%. Thus, the complementary probability that at least two people share a birthday exceeds 50%. This counterintuitive result demonstrates an important lesson in probability. When multiple events or pairs are considered simultaneously, even events with a small probability can collectively lead to a high overall chance. Our intuition tends to think of each individual comparison as insignificant, but mathematically, the sheer number of comparisons in a group quickly adds up to create a significant probability of overlap. What makes this paradox even more striking is that it challenges our everyday experience. In daily life, we rarely see probabilities working out in ways that defy our common sense, because we don't often encounter problems that involve so many overlapping possibilities. The birthday paradox, however, illustrates a core principle in combinatorics and probability theory, that the probability of at least one match increases rapidly as you add more participants, not because each individual chance is large, but because the number of comparisons grows dramatically with each additional person. Beyond being a neat party trick, the birthday paradox has practical applications in fields like cryptography and computer science. For example, in the design of hash functions and data storage, understanding the chance of collisions, where two different inputs produce the same output, is crucial. The paradox helps experts estimate how many items can be stored before the likelihood of a collision becomes significant, similar to how the shared birthday probability becomes significant in a relatively small group. Furthermore, the assumptions behind the birthday paradox are important to note. The calculations assume that birthdays are uniformly and independently distributed over 365 days, ignoring factors like seasonal birth rates or the existence of leap years. Despite these simplifications, the result remains a powerful demonstration of how probability can lead to surprising outcomes. In a broader sense, the birthday paradox invites us to rethink our assumptions about chance and randomness. It shows that even in situations that appear to be straightforward, the underlying mathematics can reveal unexpected complexities. This paradox not only provides insight into how probabilities accumulate in groups, but also serves as a gateway into more advanced topics in statistics and combinatorics, areas where seemingly simple problems can have profound and counterintuitive solutions. Ultimately, the birthday paradox is a perfect example of how mathematics can overturn our expectations. It teaches us that when dealing with probabilities, especially in scenarios involving large numbers of pairs or interactions, intuition might not always be the best guide. Instead, by methodically analyzing the situation, we discover that even a group as small as 23 people is enough to yield a 50% chance of a shared birthday, a result that is as surprising as it is enlightening. The Mandelbrot Set is a stunning example of how infinitely complex beauty emerges from incredibly simple equations. At its heart lies a deceptively straightforward mathematical rule. Start with the equation z subscript n plus 1 equals z subscript n squared plus c, where both z and c are complex numbers, and the process begins with z 0 set to 0. Despite the equation's apparent simplicity, the resulting set of points in the complex plane reveals an astonishing labyrinth of structure, a boundary so intricate that no matter how much you zoom in, you always uncover new, mesmerizing details. When you look at the Mandelbrot set as a whole, you see a large, bulbous shape with tendrils stretching out into the infinite. This shape is defined by the collection of all values of ACC, for which the sequence of numbers generated by the equation remains bounded. In other words, it never escapes to infinity. For points outside the Mandelbrot set, the iterations diverge rapidly, while those inside maintain a delicate balance of numerical behavior. It is at the boundary of these two behaviors where nature's complexity truly reveals itself. Here, the interplay between stability and chaos creates an endlessly self-similar fractal edge that captivates both mathematicians and artists. One of the most fascinating aspects of the Mandelbrot set is its fractal nature. The term fractal refers to structures that repeat themselves on various scales. In the Mandelbrot set, small copies of the entire set appear along its boundary, interwoven with intricate patterns and spiraling filaments. These miniature replicas, while not identical in every detail, carry the same fundamental structure as the whole set. This self-similarity illustrates one of the core principles of fractal geometry. From a simple generating rule, complex and recursive patterns can arise, offering a glimpse into the infinite. No matter how deep you delve into the Mandelbrot set by zooming in, you are met with a world of unexpected complexity that seems to have no end. The beauty of the Mandelbrot set is deeply intertwined with the concept of chaos and order. In the realm of dynamical systems, which study how points evolve under repeated iterations of a function, the Mandelbrot set becomes a roadmap of stability. Regions where the iterations remain bounded indicate areas of order, while the explosive divergence in other areas signals chaos. This duality is not only mathematically significant, but also resonates on an aesthetic level, embodying the idea that order and chaos are part of a continuum rather than distinct opposites. Beyond its mathematical implications, the Mandelbrot set has had a profound influence on art, science, and popular culture. The vivid images generated from the set, often rendered in rich, swirling colors that indicate how quickly points escape to infinity, serve as a bridge between abstract mathematics and visual art. These images invite viewers to ponder the underlying structure of nature itself, suggesting that complexity and beauty may emerge naturally from simple foundational rules. This interplay between abstraction and visual splendor challenges our perception of what mathematics can be. It is not merely a tool for calculation, but a portal into an infinite universe of patterns and shapes. The process of exploring the Mandelbrot set also has a very practical side. With modern computers, mathematicians and enthusiasts alike can compute and render high-resolution images of the set, exploring its depths in ways that were unimaginable before the digital age. Each zoom level reveals new patterns, often prompting further questions about the nature of convergence, divergence, and the limits of computation. What is truly remarkable is that while our computers can calculate ever deeper layers of the set, the mathematical definition remains as simple as the equation that started it all. This juxtaposition, the simple rule against an infinitely complex outcome, highlights one of the most profound ideas in mathematics, that complexity need not arise from complex origins. In a broader sense, the Mandelbrot set serves as a powerful metaphor for many systems in nature and society. It demonstrates how simple iterative processes can generate unexpected levels of complexity, a concept that appears in disciplines ranging from biology, where simple genetic rules give rise to intricate organisms, to economics, where basic principles can lead to unpredictable market behaviors. The Mandelbrot set reminds us that beneath the surface of everyday phenomena, there often lies a rich tapestry of interactions, patterns, and relationships waiting to be uncovered. Ultimately, the Mandelbrot set is more than just a collection of points in the complex plane. It is a symbol of the harmony between simplicity and complexity, an emblem of how nature can craft infinite beauty from basic principles. It challenges our understanding of the infinite and invites us to see mathematics not just as an abstract discipline, but as an art form, a way of perceiving the hidden order that governs the cosmos. In exploring the Mandelbrot set, we catch a glimpse of the deeper mathematical truths that shape our world, revealing that sometimes the simplest equations can lead us to the most profound and endlessly fascinating discoveries. The infinite monkey theorem is an intriguing and playful illustration of the surprising ways in which randomness, given enough time, can yield results that seem almost miraculous. In this case, the complete works of Shakespeare. Imagine for a moment a monkey sitting at a typewriter, randomly pounding the keys with no intention or purpose. At first glance, the idea that such chaotic, undirected actions could ever produce a coherent play, poem, or sonnet appears absurd. However, when we step into the realm of probability theory and infinite sequences, we find that given an infinite amount of time, the monkey will almost surely produce not only Shakespearean masterpieces, but every possible text you could imagine. To understand this phenomenon, it is important to recognize that the theorem is not stating that a monkey will type Shakespeare in any reasonable or practical time frame. Instead, it speaks to the nature of infinite sequences and probability. In mathematics, an event with a non-zero probability, no matter how small that probability might be, is destined to occur if given infinite opportunities, since each random keystroke has some chance, however minuscule, of contributing to the desired text. And since there are infinitely many keystrokes in an infinite sequence, the probability that every possible finite string, including the works of Shakespeare, will eventually appear is equal to 1. In the language of mathematicians, such an event occurs almost surely. At its core, the infinite monkey theorem plays with our intuition about chance and randomness. When faced with a finite sequence of random events, the odds of producing a coherent sentence or a classic play seem astronomically low. For any given short phrase, the probability might be minuscule, and for an entire play, even tinier still. However, when you extend the process into infinity, those probabilities add up in a counterintuitive way. The randomness, rather than remaining isolated and incoherent, becomes a vast canvas where every conceivable pattern is eventually painted. Each keystroke is like a drop of paint in an endless masterpiece, and the sheer volume of possibilities guarantees that the complete works of Shakespeare will not only appear, but they will be reproduced infinitely many times. This idea challenges our everyday experiences with randomness. In typical, finite situations, we are accustomed to thinking that randomness leads to chaos and disorder. Yet, the infinite monkey theorem shows that when randomness is allowed to operate over an infinite time frame, it generates a kind of order, a complete and unbounded collection of all possible texts. The theorem underlines a profound principle in probability theory. With an infinite number of trials, even events that are exceptionally unlikely in any single trial become inevitabilities. The conclusion is a striking reminder that the bounds of possibility are dramatically altered when one introduces infinity. Historically, the theorem has roots in the work of mathematicians and thinkers who were fascinated by the concepts of infinity and chance. The idea was popularized by figures like Émile Borel, who used it to illustrate the counterintuitive nature of infinite sets and measure theory. It has since become a staple example in discussions about randomness, often serving to bridge the gap between abstract mathematical theory and popular culture. Its playful imagery, a monkey, a typewriter, and Shakespeare, is powerful because it translates complex mathematical ideas into a narrative that is both entertaining and thought-provoking. It is also worth noting that the theorem does more than just imply that Shakespeare's works will eventually be produced. It actually guarantees that every possible finite sequence of characters will appear in the infinite output. This means that not only will we find coherent texts, but we would also find every variation, mistake, and alternative version of those texts. In a way, an infinite random process would contain not only masterpieces, but also every alternative history of literature, every work of literature ever written, rewritten, or imagined. It encapsulates the entire spectrum of possibility, making it a powerful metaphor for the relationship between chaos and order. The practical implications of this idea are limited by the impossibility of actually observing an infinite process. In the real world, both time and resources are finite, and no monkey, or computer simulation for that matter, can truly type for an infinite duration. However, the theorem remains a valuable conceptual tool. It helps us understand the nature of randomness, the concept of almost sure events, and how infinity operates within mathematics. It also offers a cautionary lesson. When dealing with infinite systems, our classical intuitions may fail us, and we are forced to rely on rigorous mathematical reasoning to uncover hidden truths. Moreover, the infinite monkey theorem serves as an invitation to explore larger questions about creativity, order, and the emergence of complexity from randomness. It suggests that even in a system driven solely by chance, the seeds of structure and meaning are sown if given enough opportunities to grow. This resonates with ideas in fields as diverse as evolutionary biology, where random mutations over vast timescales can lead to the emergence of highly complex organisms, and in computer science, where algorithms search for order within seemingly chaotic data. The theorem challenges us to reconsider what it means for something to be random and what it means to create something meaningful. Ultimately, the beauty of the infinite monkey theorem lies in its paradoxical nature. Randomness, which we often associate with disorder and unpredictability, guarantees the emergence of complete and coherent order over an infinite time frame. The notion that chaos can produce art, literature, and even a flawless reproduction of Shakespeare's masterpieces is not just a curiosity, it is a profound statement about the mathematical structure of the universe. It reminds us that under the surface of every random process, there is a guarantee of occurrence for every finite possibility, no matter how intricate or elaborate. In summary, while no actual monkey will ever produce a Shakespearean play in any practical sense, the theorem serves as a powerful metaphor and a testament to the unexpected ways that infinite processes work. It encapsulates the idea that given infinite time and infinite random events, not only is it possible for order to arise from chaos, it is inevitable. The infinite monkey theorem stands as one of the most captivating examples of how, when pushed to the limits of infinity, simple randomness yields an abundance of structure and creativity. A vivid reminder that in the realm of mathematics, even the wildest randomness can ultimately produce works of art. Mathematical synesthesia is a captivating phenomenon where certain individuals experience numbers, equations, or other abstract mathematical ideas as vividly colored or even imbued with tastes, sounds, or textures. Imagine looking at a page of numerical calculations and literally seeing a vibrant cascade of colors, a steady blue for the number 2, a radiant red for 3, or perhaps a soft green that outlines the curves of a quadratic equation. For synesthetes, these sensory crossovers are involuntary and consistent, painting their internal world with layers of perception that interweave logic and aesthetics. In its essence, synesthesia is a blending of the senses. While most people keep sight, sound, taste, touch, and smell in their separate domains, individuals with synesthesia experience a natural merging of these faculties. In the case of mathematical synesthesia, the normally abstract realm of numbers and symbols becomes inherently tangible. The phenomenon is not a learned or metaphorical association. Rather, it is an intrinsic aspect of their neurological wiring. When a synesthete encounters a numeral or a mathematical concept, the experience is as immediate and concrete as seeing a specific shade of color or feeling a particular texture. One of the most common forms of this condition is grapheme color synesthesia, where letters and numbers are seen in fixed, distinct colors. For these people, the number 7 might always appear as a deep violet, while the number 1 could be a bright red. This sensory overlay does more than just add a splash of color to their thoughts. It can significantly influence how they process and recall information. Many synesthetes report that the extra layer of sensory detail aids their memory and comprehension of abstract ideas. Recognizing a recurring pattern in a complex equation might become easier when each numeral carries its own hue or flavor, transforming pure calculation into an artful and multisensory experience. The origins of mathematical synesthesia, like synesthesia in general, are not yet fully understood. Current research suggests that it may stem from increased connectivity between regions of the brain responsible for processing different types of sensory information. In mathematical synesthetes, the areas that manage numerical cognition, often situated in the parietal lobe, appear to be unusually linked with parts of the visual cortex that interpret color. This neural crosstalk means that when they process numbers, an associated visual burst of color is automatically triggered. Though the exact mechanisms remain a topic of ongoing scientific inquiry, brain imaging studies have provided compelling evidence that the brains of synesthetes are wired differently from those of individuals without such experiences. The unique perspective offered by mathematical synesthesia has both aesthetic and practical implications. From an artistic viewpoint, it enriches the realm of mathematics, an area often perceived as cold or purely logical. For synesthetes, math can be a deeply personal sensory journey, an exploration where equations are as much about beauty as they are about calculation. This blending of art and science has inspired creative works in various fields, leading some to view the structured world of numbers as one teeming with visual poetry and hidden symphonies of color and taste. On a more practical level, many synesthetes find that their condition provides them with an unexpected advantage in learning and problem solving. The vivid sensory cues that accompany numbers and equations can make abstract concepts more concrete and memorable. For example, when working through an intricate proof or solving a challenging problem, the colors and tastes associated with different symbols may help in distinguishing and retaining critical details. This multisensory approach can foster a deeper, more intuitive understanding of mathematics, transforming what might otherwise be a laborious exercise into an engaging sensory experience. Despite its benefits, mathematical synesthesia also serves as a reminder of the diversity of human perception. What is often dismissed as a curious quirk is, in fact, a profound example of how our brains can reorganize sensory input in unexpected ways. It invites us to reconsider the rigidity of our sensory categories and opens up possibilities for understanding cognition on a broader, more integrated level. Rather than viewing mathematics as an isolated domain of logic, mathematical synesthesia illustrates that our experience of numbers and equations can be as rich and varied as the colors in a painting. In the broader context of human creativity, mathematical synesthesia is a striking illustration of how the fusion of seemingly disparate domains, logic and sensation, can lead to extraordinary insights. It challenges the conventional notion that mathematics is merely an abstract symbolic system, offering instead a vision of mathematics as a living, breathing art form. For those who experience these sensory crossovers, every equation is not just a problem to be solved, but a canvas painted with hues that reveal unexpected connections between the abstract and the tangible. Ultimately, mathematical synesthesia reminds us that the boundaries of perception are far more flexible than we might assume. It underscores the idea that beauty and creativity can emerge in the most unlikely of places, even in the precise language of mathematics, whether aiding in memory, sparking artistic inspiration, or simply adding a touch of wonder to the everyday act of calculation. The phenomenon of mathematical synesthesia reveals a world where logic meets art, and where every number tells a story in color, taste, and texture. The Collatz Conjecture is one of the most tantalizing puzzles in mathematics, a seemingly simple operation that has defied proof for decades and continues to inspire both amateur enthusiasts and seasoned researchers alike. Imagine taking any positive integer and applying a set of very simple rules. If the number is even, you divide it by 2. If it's odd, you multiply it by 3 and add 1. Then you repeat the process with the resulting number. The conjecture claims that no matter which number you start with, this sequence will eventually reach the number 1. Despite its straightforward appearance, no one has ever been able to prove, for all starting numbers, that the sequence always finds its way to 1. To explore this idea further, let's consider a couple of examples. Take the number 6. It is even, so we divide it by 2 to get 3. Since 3 is odd, we apply the rule for odd numbers. 3 multiplied by 3 plus 1. 1 gives us 10. Continuing, 10 is even, so we divide it by 2 and get 5. Because 5 is odd, we calculate 3 times 5 plus 1, resulting in 16. Repeating the process, we see that eventually the sequence arrives at 1. What's especially fascinating is that this pattern of rising and falling is not unique to 6. When you test many other numbers, even very large ones, they seem to follow unpredictable paths, sometimes rising very high before tumbling down toward 1. What's at the heart of the Collatz conjecture is this dichotomy between simplicity and complexity. On the surface, the rules are as straightforward as they come, yet the behavior of the sequence is remarkably erratic and has defied comprehensive understanding. Although computational tests have verified the conjecture for a vast range of numbers, into the billions and beyond, the lack of a general proof means that mathematically, the door remains open for a counterexample. Even if such a counterexample turns out never to exist, the challenge of rigorously demonstrating that every positive integer will eventually reach 1 represents a profound barrier that has withstood the best efforts of many brilliant minds. Over the years, many strategies have been attempted to crack the puzzle. Some researchers have looked for patterns in the seemingly random sequences produced by various numbers, searching for hidden structures that might reveal a common mechanism driving the outcomes. Others have tried to map the trajectories of numbers into different mathematical frameworks, hoping that a deeper insight into number theory or dynamical systems might finally shine some light on the problem. Yet, despite these extensive efforts, a complete and satisfying proof has remained elusive. In a sense, the Collatz conjecture stands as a reminder that even operations that appear elementary can harbor a complexity that transcends our standard methods of mathematical inquiry. The allure of the Collatz conjecture is partly due to its accessibility. With only one rule for even numbers and one for odd numbers, anyone with a basic understanding of arithmetic can grasp the concept, even as the full implications stretch into the realms of unsolved mathematics. This accessibility, paired with the intriguing behavior of the sequences, has made the conjecture a popular subject in both academic lectures and public discussions about the mysteries of mathematics. It invites everyone, students, hobbyists, professional mathematicians, to play with numbers and witness firsthand how simple processes can produce outcomes that are both unpredictable and mesmerizing. The broader significance of the Collatz Conjecture lies in its illustration of the gap that sometimes exists between intuition and formal proof. In everyday life, we are accustomed to the idea that if something works in a vast number of individual cases, it must be universally true. Yet mathematics teaches us that evidence gathered from countless examples does not equate to a formal, logical proof. This gap is where much of the beauty and frustration of mathematics reside. The Collatz Conjecture stands as a perfect embodiment of this tension, serving as both an accessible puzzle and a gateway to deep and challenging questions about the nature of numbers and the behavior of iterative processes. Moreover, the conjecture has a way of sparking a sense of wonder in those who study it. It prompts questions that go beyond the immediate problem. What is it about such simple operations that gives rise to complex, seemingly chaotic behavior? Could the underlying ideas behind the Collatz process be connected to other areas of mathematics, or even to phenomena in the natural world, where simple rules often lead to unexpected patterns? As mathematicians continue to probe these questions, the Collatz Conjecture remains at the crossroads of number theory and dynamical systems, inspiring research that may one day uncover new layers of understanding about how order and chaos can coexist in mathematical systems. In the end, the Collatz Conjecture is a beautiful example of how mathematics can be both delightfully simple and profoundly deep. It challenges us to look at numbers not just as static entities, but as part of dynamic processes that reveal surprising complexity over time. Even though no one has yet provided a complete proof of its universal truth, the conjecture persists as an enduring mystery, a testament to the idea that even in the realm of pure logic and rigorous proof, there is space for wonder, exploration, and the unexpected. Benford's law is a fascinating and somewhat counterintuitive mathematical observation that in many naturally occurring datasets, the number 1 appears as the leading digit far more frequently than any other digit. This phenomenon might seem mysterious at first, because most of us would expect the digits 1 through 9 to occur as the first digit with roughly equal probability. However, when you examine datasets such as financial figures, population numbers, river lengths, or even physical constants, you find that about 30% of the time, the first digit is 1, while larger digits like 9 appear as the first digit less than 5% of the time. The explanation behind this curious distribution lies in the mathematics of logarithms. Benford's law states that the probability PD of a digit d, where d is any number from 1 to 9, being the leading digit, is given by the formula PD equals log base 10 of 1 plus 1 over d. For d equal to 1, this formula computes to log base 10 of 2, which is approximately 0.301 or 30.1%. For d equal to 9, it becomes log base 10 of 10 divided by 9, coming out to about 0.046 or 4.6%. This logarithmic distribution naturally emerges in many datasets that span several orders of magnitude because the numbers are not spread uniformly. Instead, they grow exponentially, and the scale on which the data is measured is logarithmic. When you transform the data using a logarithm, the non-uniformity in the appearance of digits becomes clear. Historically, the curious regularity of first digits was first noted by Simon Newcomb in the 19th century, when he observed that the earlier pages of logarithm tables, those beginning with lower numbers, were worn out more quickly than the later pages. Later on, Frank Benford conducted empirical studies across a wide range of data and confirmed that this pattern held true in many contexts, lending his name to the law. What makes Benford's law even more intriguing is its scale invariance. This means that if you multiply every number in a dataset by a constant, the distribution of the first digits will remain the same. This attribute is rare and highlights an underlying uniformity that transcends the specifics of the measurements. One of the most compelling aspects of Benford's law is its practical application, especially in the realm of fraud detection and forensic accounting. Since genuine data, such as tax records or financial statements, often follow this logarithmic distribution, significant deviations from Benford's expected frequencies can serve as red flags, potentially indicating manipulation or fabrication. Auditors and forensic analysts use these insights to develop tests and algorithms that can sift through massive amounts of data to pinpoint suspicious anomalies. In this way, a mathematical curiosity becomes a powerful tool in ensuring financial integrity and transparency. Despite its success in a variety of applications, Benford's law does not hold for every dataset. It tends to work best with numbers that are not artificially bounded or restricted by human conventions. For instance, datasets like telephone numbers or social security numbers, which are often assigned or formatted according to specific rules rather than arising naturally, do not exhibit Benford behavior. This limitation underscores an important point. Benford's law is a reflection of the natural variability and the multiplicative processes that generate many types of data in the real world. The broader significance of Benford's law lies in how it challenges our intuitive sense of randomness and uniformity. Our everyday experience might lead us to assume that without any compelling bias, digits should appear uniformly. However, the law reminds us that when numbers describe quantities in nature that span several orders of magnitude, the dynamics of growth and division often result in a bias towards smaller digits. This insight forces us to re-examine our assumptions about what normal or random really means when dealing with numerical data. Moreover, Benford's law can be seen as a gateway to deeper questions about the nature of numbers, scale, and information. It provides a striking example of how simple logarithmic relationships can give rise to complex and unexpected outcomes. The observation that a single digit, 1, dominates the leading positions of so many datasets is not merely a numerical curiosity, but a reflection of the inherent structure of the natural and social sciences. Whether it's the distribution of city populations, the lengths of rivers, or the financial figures produced by millions of transactions, there is an underlying order that Benford's law helps to reveal. In a broader sense, this law exemplifies the beauty of mathematics by showing how a simple formula can unlock patterns in the complex, seemingly chaotic world around us. It connects abstract mathematical theory with practical, real-world applications, bridging the gap between pure and applied mathematics. The mystery of the prevalence of the number 1 invites us to appreciate how deep insights often lie hidden in the most unexpected places, and how mathematical reasoning can illuminate our understanding of the universe. Ultimately, Benford's law serves as a reminder that the world of numbers holds secrets that defy our everyday intuitions. It encourages us to look beyond the obvious and to explore the elegant structures that govern even the mundane details of life. The fact that such a simple principle can reveal so much about the way data behaves and even help expose fraudulent activities underscores the enduring power of mathematics to uncover hidden truths and bring order to the apparent chaos. The four-color theorem is one of those delightful results in mathematics that at first glance appears almost magical. No matter how complex a map might seem, you never need more than 4 colors to ensure that no 2 adjacent regions share the same color. This theorem, which emerged from the study of cartography and graph theory, tells us that if you take any map, whether it represents countries on Earth, states, or even abstract regions on a board, you can color each region with one of just 4 distinct colors, so that any 2 regions with a common boundary are colored differently. The idea is simple yet profound, challenging our assumptions about complexity by showing that a universal simplicity underlies even the most varied and intricate maps. The origins of the 4-color theorem can be traced back to a problem posed by Francis Guthrie in the mid-19th century, when he was trying to color the counties of England and realized that 4 colors were sufficient to prevent any neighboring counties from sharing the same hue. This observation sparked significant interest among mathematicians, as it suggested that there might be a deeper, underlying principle governing such colorings. Over the next 100 years, numerous mathematicians attempted to prove the theorem using traditional techniques, and while some proposed proofs initially appeared promising, they eventually revealed unforeseen flaws. The challenge was not only to find a method that worked for a given map, but to establish a proof that applied to every conceivable arrangement of regions on a plane. To understand why 4 colors are enough, it is helpful to think of the problem in terms of graph theory. Every map can be converted into a graph by representing each distinct region as a vertex and drawing an edge between 2 vertices if the corresponding regions share a common boundary. In many cases, this transformation reduces a messy, irregular map into an abstract network that follow specific rules. Mathematicians discovered that these planar graphs that can be drawn on a plane without any of the edges crossing, have a surprising property. They can always be colored using at most 4 colors. This insight is rooted in what is known as the planarity of the graph, and the fact that the regions in a typical map are arranged in a way that limits the number of neighbors any one region can have. After many decades of effort, the theorem was finally proven in 1976 by Kenneth Appel and Wolfgang Hucken, though their proof marked a significant turning point in the history of mathematics because it was the first major theorem to be proven with extensive computer assistance. Appel and Hucken's strategy involved reducing the infinite number of possible maps to a finite number of cases that could be checked by a computer. Although some mathematicians were initially skeptical of a proof that relied on so many computer-generated verifications, over time the community has come to accept that the proof, while not as elegant as a traditional human-derived proof, was both rigorous and complete. Their work opened up new discussions about the role of computers in mathematics, prompting debates about the nature of proof and the future of mathematical inquiry in the digital age. What makes the 4-color theorem so compelling goes beyond the surprising fact that just 4 colors are sufficient. It illustrates an important philosophical point, that the world, however complex and diverse it appears, sometimes obeys very simple underlying laws. This idea resonates in many areas of science and art, suggesting that beneath the apparent chaos of everyday phenomena, there is an inherent order that can be uncovered through careful analysis. The theorem also has practical applications. For instance, it is used in designing efficient algorithms for tasks such as scheduling, frequency assignment in wireless networks, and even in solving puzzles and games that require a systematic approach to conflict resolution. Moreover, the theorem exemplifies the beauty of mathematical abstraction by translating a real-world challenge, coloring a map, into a problem about graphs and planar structures. Mathematicians have been able to explore the interplay between discrete mathematics and geometry. This fusion of ideas not only advances our theoretical knowledge, but also has the potential to lead to innovations in computational methods and problem-solving strategies. The concepts developed while studying map coloring extend into diverse fields, including computer science and topology, further demonstrating that even problems with a seemingly mundane origin can have far-reaching implications. In the end, the four-color theorem stands as a testament to the power of mathematical reasoning to uncover hidden simplicity in the most unexpected places. It reminds us that rigorous inquiry and sometimes even technological advancements, such as the use of computers in proofs, can break through barriers that once seemed insurmountable. Although the theorem deals with the practical question of coloring maps, its significance reaches into the heart of what mathematics is all about: finding order, establishing connections, and seeing beauty in the logical structure of the world around us. Ultimately, the realization that no map on Earth requires more than four colors is not only a triumph of human intellect, but also a vivid illustration of how mathematics can reveal a surprising and elegant simplicity that lies beneath the surface of everyday life. The prisoner's dilemma is a classic example in game theory that reveals how individual rationality can lead to collective outcomes that seem counterintuitive, especially when trust and betrayal come into play. Imagine two individuals arrested for a crime, forced into separate rooms where they cannot communicate, and given a choice: betray the other by testifying that the other committed the offense, or remain silent. The rules are clear. If both stay silent, they each receive a light sentence. If one betrays while the other remains silent, the betrayer goes free while the silent one suffers a harsh penalty. And if both betray each other, they both receive a moderately severe sentence. This setup creates a paradox, because while mutual cooperation would yield the best collective outcome, each prisoner has an incentive to betray, since doing so minimizes their own risk if they suspect the other might betray. This logic is encapsulated in the concept of the Nash equilibrium, a cornerstone of game theory. In the one-shot prisoner's dilemma, each prisoner's decision is made without knowing the other's move, and the best strategy for both, assuming they act purely out of self-interest, is to betray. Even though mutual betrayal results in a worse outcome for both compared to mutual cooperation, the fear of being the only one who cooperates, and thereby suffering the worst possible punishment, pushes each prisoner toward defection. Mathematics here exposes a counterintuitive truth. What is best for the individual in a one-time interaction may lead to a collectively suboptimal result. One of the most intriguing aspects of the prisoner's dilemma is how it extends far beyond a criminal interrogation scenario and applies to countless real-life situations, from business negotiations to international diplomacy. In competitive markets, for example, companies face choices that resemble the dilemma. If they collaborate on fair pricing or environmental standards, all benefit, yet the temptation to undercut a competitor for short-term gain can lead to mutually harmful outcomes. Similarly, nations engaged in an arms race find themselves trapped in a situation where building more weapons seems individually rational, even though de-escalation would lead to a more secure and stable world for all. Over time, researchers have studied repeated or iterated versions of the prisoner's dilemma, where players engage in the game multiple times. In these scenarios, the possibility of future interactions changes the dynamics dramatically. When the game is played repeatedly, a strategy based solely on betrayal in each round may no longer be optimal. Instead, cooperation becomes more appealing because building trust and a reputation for reciprocity can lead to better long-term outcomes. This is why phenomena such as tit for tat have emerged as effective strategies in iterated dilemmas. Players start by cooperating, then mimic their partner's previous move, rewarding cooperation and punishing betrayal in equal measure. The mathematical models of repeated games show that while short-term incentives can favor defection, a longer horizon can encourage a willingness to cooperate, thereby revealing the surprising logic behind trust. The interplay between trust and betrayal within the prisoner's dilemma has also led to profound insights into human psychology and social behavior. It underscores the idea that our decision-making is not purely based on isolated rational calculations. Emotions, past experiences, and the anticipation of future interactions all play critical roles in how we choose to cooperate or defect. Humans, unlike the idealized, perfectly rational agents of classical game theory, often consider factors such as fairness and the potential for reciprocation. In many cases, what might appear mathematically suboptimal in a one-shot game can become the most rewarding strategy when social context and repeated interactions are taken into account. Moreover, the prisoner's dilemma provides a framework for exploring how institutions and social norms can mitigate the downside of purely self-interested behavior. Societies that establish trust through enforceable contracts, transparent communication, and shared values effectively transform a single round of the dilemma into an iterated game where cooperation is more likely to thrive. Legal systems, codes of conduct, and even the prospect of reputational harm serve as mechanisms to align individual interests with the greater good. Mathematics, by modeling these interactions, helps us understand why certain social structures work better than others in promoting collaboration and reducing conflict. Beyond its practical applications, the prisoner's dilemma invites us to reflect on the delicate balance between competition and cooperation that defines much of human interaction. It illustrates that there is no absolute answer on whether trust or betrayal is the superior strategy. It depends on the context, the number of interactions, and the underlying assumptions about human behavior. While the Nash equilibrium in a one-off dilemma suggests that betrayal is inevitable, the richer, more nuanced analysis of repeated interactions shows that trust can indeed emerge as a rational strategy over time. This duality captures the tension inherent in many real-world situations, where the lure of immediate gain conflicts with the benefits of long-term partnership. In essence, the prisoner's dilemma is a microcosm of the challenges we face in a complex world. It reveals that the pursuit of individual self-interest, when carried out in isolation, can inadvertently create situations where everyone loses out. Mathematics lays bare this paradox, showing that the path to optimal outcomes often requires a willingness to take risks on trust and to value long-term relationships over short-term benefits. The delicate interplay between cooperation and competition, as modeled by the prisoner's dilemma, offers a powerful lens through which we can analyze and perhaps improve the systems that govern social interactions and economic behavior. The Arrow of Time paradox raises profound questions about whether time really has a preferred direction. and it does so by juxtaposing our everyday experience with the surprising symmetry of the fundamental laws of mathematics and physics. On one hand, our experience is unmistakable. Time seems to flow steadily from a fixed past into an uncertain future, and events irreversibly proceed toward ever higher levels of disorder. We remember the past, not the future, and every cause appears to lead to an effect in one direction. Yet when we look at the equations that underpin classical mechanics, or even quantum mechanics, we find that many of them are time reversible. That is, they work equally well if time were to run backward. This discrepancy between the mathematical symmetry of microscopic laws and the macroscopic arrow we observe creates a paradox that has intrigued mathematicians, physicists, and philosophers alike. To delve into this paradox, consider the nature of physical laws at the most fundamental level. Newton's laws of motion, for instance, have no inherent preference for time moving forward. If you filmed a collision between two billiard balls and played it in reverse, the underlying equations would still hold true, suggesting that the process is mathematically reversible. This idea extends into many areas of physics, where time reversal symmetry indicates that the equations do not single out a direction. If the microscopic dynamics are essentially indifferent to the flow of time, one naturally wonders why our macroscopic world is not as indifferent. Why does a glass fall and shatter, but never reassemble itself spontaneously? This dissonance between micro and macro forces us to look deeper into what actually distinguishes the past from the future. The key to resolving this paradox lies in the concept of entropy, as formulated in the second law of thermodynamics. Entropy is a measure of disorder in a system, and the second law states that in a closed system, entropy will tend to increase over time. In other words, while the equations governing individual particle dynamics are time-symmetric, when you consider the collective behavior of a vast number of particles, the likelihood of transitioning from a state of high entropy, disorder, back to a state of low entropy, order, becomes astronomically small. This statistical inevitability is what gives rise to the arrow of time. While the mathematics permits reversibility, the overwhelming probability is for systems to move toward increased disorder. Thus, our macroscopic experience of time's direction is not enforced by the underlying laws themselves, but rather emerges as a statistical phenomenon from the initial conditions of our universe and the sheer number of particles involved. Consider an idealized example. Imagine an isolated gas in a container. The microscopic behavior of each gas molecule is random and, in theory, reversible. Yet, if you start with the gas in one corner of the container, the molecules will quickly spread out to fill the available space, increasing the system's entropy. The reverse process, where all the gas molecules spontaneously reconvene in one corner, is not forbidden by the laws of physics, but the probability of such an event is so minuscule that it is effectively impossible over the lifetime of the universe. This gap between possibility and probability is where the arrow of time comes into focus. It is not that the equations of motion dictate a forward march of time. Rather, the overwhelmingly likely behavior of large systems steers them towards states of higher disorder. In addition to the thermodynamic arrow of time, there are other arrows that seem to indicate a preferred direction. For example, the psychological arrow of time, our experience of time as flowing from past to future, is intimately connected with the way memory works. We remember what has happened, but we have no access to what is yet to occur, because our memories are formed out of irreversibly recorded information, a process that itself increases entropy. Similarly, the cosmological arrow of time, which reflects the expansion of the universe from an initial, highly ordered state, such as the Big Bang, also imposes a temporal direction on the large-scale structure of the cosmos. Mathematics and physics together help us understand these arrows not as intrinsic properties of time itself, but as emergent phenomena shaped by initial conditions and probabilistic rules governing large numbers of interacting particles. This paradox, then, invites us to re-examine our assumptions about time. While the differential equations that dictate the motion of planets or particles do not distinguish between the past and the future, the collective behavior of these systems and the nature of the initial conditions of the universe creates the illusion of a one-way flow. It challenges us to think about time as an emergent property, one that arises from the complex interplay between microscopic symmetry and macroscopic asymmetry. Mathematics does not provide a simple answer to whether time fundamentally flows, but it offers a framework in which this puzzling behavior can be rigorously understood in terms of probability, statistical mechanics, and the structure of the universe. Ultimately, the arrow of time paradox underscores a deeper mystery, that the simple, elegant laws of nature, when scaled up, lead to phenomena that are anything but reversible. It is a reminder that reality often harbors profound complexities beneath seemingly straightforward principles. Mathematics serves as our lens to peer into this paradox, showing us that while time's arrow might not be written into the fabric of fundamental laws, it is an emergent feature of the universe, a statistical certainty born from chaos and order intertwined. In contemplating this, we gain a richer appreciation for the subtle dance between possibility and probability that shapes our perception of reality, urging us to explore further the enigmatic nature of time itself. Cantor's diagonal argument is one of the most elegant and profound ideas in mathematics that reshaped our understanding of infinity. Before Cantor's groundbreaking work in the late 19th century, many mathematicians assumed all infinities were essentially equivalent. That infinity was simply a never-ending collection of elements with no fine distinctions in size. However, Cantor's ingenious argument showed that not all infinities are created equal. Some infinities are indeed larger than others. Imagine for a moment that you have a list, a complete catalogue of all the natural numbers, 1, 2, 3, 4, and so on into infinity. In this case, we say the set of natural numbers is countably infinite because you can, in principle, enumerate each element one by one, even if the process goes on forever. Now, consider the set of all real numbers between 0 and 1, which at first seems to be another kind of infinite set. Intuitively, one might think that since both the natural numbers and the real numbers stretch out indefinitely, they might be the same size. Cantor, however, demonstrated that the infinity of the real numbers is strictly larger, a revelation that took mathematicians by surprise. Cantor's diagonal argument proceeds by contradiction. Suppose that it were possible to list all the real numbers between 0 and 1 in a sequence, each expressed in its decimal form. Imagine writing these numbers one under the other, where each row represents a different number in our hypothetical list. Now, construct a new number digit by digit. For the first digit of this new number, take a digit different from the first digit of the first number in the list. For the second digit, choose a digit different from the second digit of the second number, and continue this process indefinitely. The resulting number is constructed in such a way that it differs from every number in the original list in at least one decimal place. Thus, no matter what list you devise, this new number cannot be part of it, because it was intentionally made to escape the entire enumeration. This contradiction implies that the original assumption that all the real numbers between 0 and 1 could be listed and therefore are countable is false. In other words, there must be more real numbers than there are natural numbers, and the infinity associated with the continuum of real numbers is strictly greater than the infinity of the natural numbers. What makes this argument particularly fascinating is its simplicity and generality. Cantor did not need to construct a complex machine or invoke abstract philosophical concepts. He simply showed that by a clever rearrangement, the diagonalization, you can always find an element that was missed in any supposed complete list. This method not only proves that the set of real numbers is uncountable, but also lays the groundwork for understanding a whole hierarchy of different infinities. The size of the set of natural numbers is denoted by the cardinal number Aleph null, while the size of the continuum, the real numbers, is denoted by a larger cardinality, often associated with the symbol C or 2 to the power of Aleph null. Cantor's work challenged the very foundations of mathematics by introducing the idea that infinite sets have different sizes or cardinalities. It opened up a whole new branch of mathematical research, set theory, which has since become a fundamental tool in modern mathematics. This discovery has far-reaching implications not only in pure mathematics, but also in areas such as computer science, logic, and even philosophy, where questions about the nature of infinity continue to inspire debate and inquiry. Moreover, Cantor's diagonal argument resonates on a deeper level by revealing that the intuitive notion of more or bigger is not restricted to finite objects. In a finite world, it's easy to compare sizes, but Cantor's insight shows that our ideas about size can be extended to the infinite realm in a rigorous and meaningful way. This idea that some infinities can be larger than others is both counterintuitive and profoundly beautiful. It reminds us that mathematics often defies our common sense, revealing layers of complexity and structure hidden within concepts that, on the surface, appear simple or even mundane. The legacy of Cantor's diagonal argument endures because it fundamentally shifts the way we think about infinity, proof, and logic. It underscores the power of a well-constructed proof to overturn long-standing assumptions and to open up new vistas of understanding. By showing that even within the infinite, there is a hierarchy, a rich, ordered structure, Cantor invited mathematicians to explore the infinite with renewed vigor and helped to establish modern set theory as a cornerstone of contemporary mathematics. In essence, Cantor's diagonal argument is a brilliant demonstration of how mathematics can reveal unexpected truths about the world, challenging our perceptions and expanding our conceptual horizons. It teaches us that sometimes the most profound discoveries are not found in the complexity of our tools, but in the simple, clear insight that changes the way we view the universe, reminding us that even the infinite is full of surprises. The Pigeonhole Principle is a deceptively simple concept that reveals how, under certain conditions, randomness inevitably creates order. At its core, the principle states that if you have more objects, or pigeons, than containers, or pigeonholes, then at least one container must hold more than one object. For example, if you have 13 pigeons trying to nest in 12 pigeonholes, at least one pigeonhole must contain at least 2 pigeons. This intuitive idea is a cornerstone of combinatorial mathematics and illustrates that no matter how haphazard the distribution might appear, inherent structure and order must emerge. Consider a scenario in which you randomly distribute a large number of items among a limited number of categories. One might initially expect that chaos will prevail, and nothing will stand out as particularly organized. However, the Pigeonhole Principle tells us that once the number of items exceeds the number of categories, repetition is not just possible, it's guaranteed. For example, if you have 367 people gathered in a room, since there are only 366 possible birthdays, including February 29th, the principle ensures that at least 2 people will share a birthday. This result, seemingly mundane, actually reinforces the notion that within randomness lies an inevitable order dictated by mathematical certainty. One of the striking implications of the Pigeonhole Principle is that it doesn't require any detailed knowledge about the arrangement of the objects. The principle is purely a counting argument. It doesn't matter whether the pigeons are arranged in a neat line or scattered randomly across the pigeonholes. Regardless of the method used to distribute the objects, if you exceed the number of containers, some container must hold multiple objects. This universality is what gives the Pigeonhole Principle its remarkable power. It guarantees order in a very broad array of contexts without having to rely on complicated rules or probability distributions. Mathematicians have harnessed the Pigeonhole Principle to solve problems that at first glance seem counterintuitive. In number theory, for instance, the principle can be used to show that in any group of people, there will always be 2 whose number of acquaintances is the same. In computer science, it often underpins proofs regarding data collisions in hashing algorithms. When you try to store more data elements than there are unique hash values available, collisions become inevitable. This principle forces us to acknowledge that despite the apparent randomness in data assignment, there is an underlying structure that governs how elements cluster together. Moreover, the Pigeonhole Principle is not just a statement of inevitability. It often offers a surprising insight into the beauty of mathematical structure. It serves as a reminder that the constraints of a system can lead to unexpected regularities. In many natural and social systems, limited resources or predetermined boundaries result in patterns that might seem emergent or even orderly. For example, consider how stars in a galaxy or organisms in an ecosystem might distribute themselves. Even if the positioning appears random, the sheer fact that the number of entities far exceeds the available positions or niches means that some level of clustering or repeated configurations will naturally occur. In this way, the Pigeonhole Principle suggests that order is not the absence of randomness, but rather an inevitable consequence of finite limits within any system. The idea also has philosophical implications regarding our understanding of randomness itself. Often, randomness is perceived as disorderly and without structure, but the Pigeonhole Principle shows that order can naturally arise from random processes given the right constraints. It implies that even in the absence of a deliberate organizing force, inherent mathematical limitations will impose a form of order on the outcomes. For instance, if you randomly generate a long sequence of digits, while each digit may seem arbitrary, the Pigeonhole Principle guarantees that certain patterns will repeat if the sequence is long enough. This insight underpins many phenomena in statistics and natural sciences, where seemingly random data exhibits clear and predictable patterns once analyzed through a mathematical lens. Beyond its direct applications, the Pigeonhole Principle invites us to appreciate the elegance of mathematical thought. It distills the complexity of large, random systems into a simple yet profound truth. When you exceed the capacity of a system's available slots, repetition must occur, and with it, order. This principle is a powerful tool not only in solving puzzles and proving the existence of certain configurations, but also in inspiring deeper reflections on how we perceive randomness and order in the world around us. It tells us that beneath the surface chaos, there is a steadfast framework, a mathematical inevitability that orchestrates the way elements distribute themselves. In conclusion, the Pigeonhole Principle, with its straightforward premise, demonstrates that randomness and chaos are not antithetical to order. Instead, because of the inherent limitations imposed by finite structures, order arises inevitably when these limits are exceeded. This elegant truth is a testament to the profound insights that simple mathematical concepts can provide, and offers us a glimpse into the underlying order that shapes not only abstract numbers, but also the natural and social phenomena we observe every day. The black hole information paradox is a striking conundrum at the intersection of quantum mechanics and general relativity, where mathematics forces us to question whether information can really vanish from the universe. In everyday terms, we think of black holes as cosmic vacuum cleaners that suck in everything, including light, with no chance of escape once something passes the event horizon. Yet, according to the principles of quantum mechanics, information about any physical system must be preserved, a concept known as unitarity. This tension between what our gravitational theories predict and what quantum mechanics demands creates a paradox. If a black hole ultimately evaporates by emitting Hawking radiation, does the information about everything that fell into it disappear forever? On one side of the paradox is Stephen Hawking's discovery that black holes are not entirely black. They emit radiation due to quantum effects near the event horizon. Hawking radiation is thermal and appears to lack any detail about the matter that formed the black hole, which implies that, as the black hole evaporates, it seemingly erases information. In contrast, the unitarity principle in quantum theory insists that the evolution of any system is reversible and that the complete information about the system's past and future states is conserved. Mathematically, the discrepancy is startling. How can a process that appears irreversible, resulting in pure, uncorrelated radiation, be reconciled with a theory where information is never lost? To address this, researchers have devised ingenious mathematical frameworks. One promising approach is the holographic principle, which posits that all the information contained within a volume of space can be represented by data encoded on its boundary. In the context of black holes, this suggests that every bit of information swallowed by a black hole might be stored at the event horizon rather than disappearing into a mysterious singularity. Techniques from string theory and the ADS-CFT correspondence, a duality that equates a gravitational theory in a higher dimensional space-time with a quantum field theory on its lower dimensional boundary, offer a mathematical route to preserve unitarity. In these models, the complex correlations present in the Hawking radiation could, in principle, encode the information that was thought to be lost. The challenge becomes even more acute when we consider the dynamics of entanglement. Recent breakthroughs have applied methods from quantum information theory, showing that the geometry of space-time itself might be an emergent phenomenon arising from the entanglement structure of quantum states. These ideas imply that there could be deep mathematical ties between the way information is shared among particles and the structure of the black hole's event horizon. In turn, entanglement entropy, a measure of quantum correlations, may play a crucial role in understanding how information is woven into the fabric of Hawking radiation, subtly escaping the fate of oblivion predicted by classical general relativity. Despite these promising developments, the paradox remains unresolved in many respects. Some theorists suggest the existence of firewalls at the event horizon, hypothetical zones of extreme energy that could break the smooth passage of information in a way that defies our current understanding of space-time continuity. Others argue for models of black hole complementarity, where what one observer perceives as lost information is encoded in an intricate web of quantum correlations that another observer might decode in a complementary description. Mathematically, these debates hinge on subtle questions about how to rigorously define and track information in a system where the classical concept of space-time breaks down, and they push the limits of our computational and conceptual tools. The black hole information paradox doesn't just represent an isolated problem in theoretical physics. It's a profound challenge that forces mathematicians and physicists to rethink the foundational principles of the universe. At its heart, the paradox confronts us with a tension between the perfectly deterministic, reversible equations of quantum mechanics and the seemingly irreversible phenomena dictated by general relativity. The mathematical journey into resolving this paradox has spurred new theories, inspired innovative approaches in quantum gravity, and even reshaped our notions of causality and time itself. Ultimately, by mathematically confronting what happens when information appears to vanish into a black hole, the paradox invites us to explore the deepest questions about the nature of reality. It compels us to consider how ordered, quantifiable information can emerge from the chaotic interplay of quantum fluctuations and gravitational collapse. While a complete resolution remains elusive, each mathematical insight and every model that brings us closer to understanding hints at a universe more interconnected and subtle than our classical intuitions would suggest. The quest to resolve the black hole information paradox continues to be one of the most captivating and challenging frontiers in modern physics, a testament to the power of mathematics to reshape our understanding of the cosmos, even when confronting what might at first appear as the ultimate cosmic mystery. The Klein bottle is one of those remarkable objects in mathematics that forces us to question our everyday notions of inside and outside. At first glance, the idea of a bottle with no distinct interior or exterior seems utterly paradoxical. How can a container, by definition meant to hold something, have no clear separation between its inside and its outside? Yet in the realm of abstract mathematics, such an object not only exists, but is perfectly well defined. Imagine a standard bottle. It has an inner cavity where you could pour water and an outer surface that you can touch. The Klein bottle, however, is constructed in such a way that if you were to follow its surface continuously, you would eventually return to your starting point, having traversed what would conventionally be considered both the inside and the outside, without ever crossing an edge or boundary. This is because the Klein bottle is a non-orientable surface. It doesn't have two distinct sides. In a sense, every point on the surface is alike. There's no inside and no outside, as we typically understand these concepts. The construction of a Klein bottle starts with a simple idea. Consider a rectangular strip where one pair of opposite edges is identified directly, like forming a cylinder or a tube. Now for the other pair of edges, rather than gluing them together in the same orientation, You attach them with a twist. This twist is what creates the non-orientable property, much like how a Mobius strip forms a one-sided surface. But unlike the Mobius strip, which has an edge, the Klein bottle has no boundary. It's a closed surface. This property implies that as you move along the surface, you can cross over what seems to be a barrier between inside and outside without ever encountering an edge. However, there's a catch. While the Klein bottle exists as a mathematical abstraction, it cannot be embedded in our familiar three-dimensional space without intersecting itself. In 3 dimensions, any attempt to create a true Klein bottle results in an inevitable self-intersection, a kind of crossover that breaks the smooth continuity that the abstract Klein bottle possesses. To construct a true, non-intersecting Klein bottle, we need to venture into 4-dimensional space. In 4 dimensions, the Klein bottle can exist without self-intersections, preserving its intriguing topological properties completely. This discrepancy between mathematical possibility and physical realization highlights a recurring theme in the study of higher dimensions. Mathematics allows us to explore concepts far beyond our direct sensory experience. The Klein bottle exemplifies how a single, simple set of rules can produce an object that defies our intuitive understanding of physical space. It not only challenges our conventional ideas about objects and boundaries, but also provides a concrete example of how higher dimensional thinking can reveal entirely new perspectives on familiar ideas. Beyond its theoretical allure, the Klein bottle has broader implications in various fields. In topology, the branch of mathematics that studies properties preserved through deformations, twistings, and stretchings, the Klein bottle serves as a classic example of a non-orientable surface. Its properties inform us about how spaces can be connected in unusual ways, which has ramifications in understanding complex systems and even in modern physics. The concept of non-orientability plays a role in theories about the fabric of the universe, particularly in areas like string theory, where the topology of space-time may be far more complicated than our everyday experience suggests. Moreover, the paradox of the Klein bottle invites us to reflect philosophically on the nature of order and boundaries. Just as the Klein bottle blurs the line between inside and outside, many phenomena in nature and society resist simple, binary categorizations. It reminds us that what we perceive as opposites might, under a deeper examination, be part of a seamless continuum. In this way, the Klein bottle is not merely a mathematical curiosity, it is a symbol of the power of abstraction to reshape our understanding of reality. In summary, the Klein bottle exemplifies a profound paradox. It is mathematically conceivable and beautifully consistent, yet it eludes physical realization in 3 dimensions. Its existence challenges our preconceptions and underscores the vast, often counterintuitive landscape of higher dimensional geometry. By showing that a simple alteration in how we glue edges together can dissolve the boundary between inside and outside, the Klein bottle stands as a testament to the elegance and depth of mathematical thought, a reminder that sometimes the most bewildering ideas arise from the simplest of processes. Optical illusions are a fascinating intersection where mathematics, psychology, and neuroscience meet, revealing just how our brains interpret and sometimes misinterpret the visual information that floods in from our environment. At the heart of many optical illusions lies a set of underlying mathematical principles that govern how light, lines, angles, and shadows interact to create images that can trick our perception. One common example is the way parallel lines appear to converge in a drawing of a railroad track, an effect known as linear perspective. This phenomenon is rooted in projective geometry, the branch of mathematics that deals with properties of figures that remain invariant under projection. Our brains, having evolved to understand the world in 3 dimensions, use these geometric cues to reconstruct spatial depth on a 2-dimensional surface, sometimes leading to surprising or conflicting interpretations. Another rich source of optical illusions comes from the exploitation of symmetry and asymmetry. Our visual system has a strong preference for symmetry, which is often a marker of order or natural beauty. When a pattern is slightly disrupted, a gap in a series of lines, or a change in texture, our brains struggle to reconcile this inconsistency with our internal model of what a harmonious pattern should look like. Mathematically, this can be related to the idea of symmetry groups, where operations like rotations or reflections leave an object unchanged. When an image violates these symmetries, it creates a visual tension that can lead to surprising effects, such as the perception of motion or depth where none actually exists. For instance, consider the famous rotating snakes illusion, where static images appear to ripple and move, a phenomenon that has been linked to the way our visual systems process contrasts and edges, something that can be modeled using differential equations and group theory. Illusions also highlight the role of spatial averaging and integration, processes that are fundamentally mathematical in nature. Our eyes and brains integrate vast amounts of information across different regions of the visual field. This integration, however, does not always happen in a perfectly linear fashion. Non-linear processes, which are common in mathematical modeling, often come into play. A classic example is the Ebbinghaus illusion, where a central circle appears larger or smaller depending on the size of the surrounding circles. Research suggests that our brains compare relative rather than absolute sizes, a sort of implicit normalization that can be described using scaling factors and ratio analysis. The inherent nonlinearity in our perceptual system means that the same stimulus can be interpreted in dramatically different ways depending on context, much like how a slight tweak in a mathematical function can lead to significant differences in its graph. Furthermore, our perception of optical illusions is deeply influenced by the brain's process of inference, a kind of internal mathematical computation that fills in missing information based on prior knowledge and expectation. The Gestalt principles, for instance, outline how the brain naturally organizes visual elements into groups and patterns, emphasizing notions such as proximity, similarity, and continuity. These principles can be seen as heuristic algorithms, akin to mathematical rules, that help our brains quickly construct a coherent picture of the world. However, when an image is designed to intentionally break these rules, it forces the brain to make conflicting calculations. The result is an image that is simultaneously interpreted in 2 incompatible ways, a duality that is both perplexing and aesthetically intriguing. One of the most evocative examples of this kind of mathematical interplay is found in ambiguous figures like the Necker cube or the famous duck-rabbit illustration. These images harness simple geometric properties, lines, angles, and intersections, to create multiple, equally valid interpretations. From a mathematical standpoint, these illusions exploit the fact that the projection of a 3-dimensional object onto a 2-dimensional plane can yield different reconstructions depending on the assumptions made by the observer. When our brains lack sufficient cues to unequivocally determine the configuration, they default to switching between different possible solutions, much like how an algorithm might iterate through different potential optimizations until a stable solution is found. The role of mathematical modeling in understanding these optical phenomena extends into the realm of modern computational neuroscience as well. Researchers use concepts from probability theory and statistics to model how neurons respond to various visual stimuli. For instance, Bayesian inference, a mathematical framework that updates the probability of a hypothesis as more evidence becomes available, is frequently used to model how our brains interpret noisy or ambiguous sensory information. In the context of optical illusions, Bayesian models help explain why our brains sometimes choose an interpretation that is at odds with the physical reality. Our perceptual system is essentially balancing on the edge of uncertainty, constantly updating its internal models based on both the new inputs and its prior experiences. This dynamic process is a potent illustration of how mathematical principles govern even the most subjective aspects of human experience. Ultimately, the mathematics behind optical illusions serves as a reminder of the incredible complexity and efficiency of our brains. What appears to be a simple trick of the eye is, in fact, a complex interplay of geometric, algebraic, and probabilistic computations that enable us to navigate and understand the world. The same mathematical principles that allow us to build bridges or predict the trajectories of celestial bodies are at work in our own minds, constructing our perception of reality. Optical illusions, then, are not just visual curiosities. They are windows into the hidden calculations that underpin every moment of our conscious experience. They demonstrate that sometimes the errors our brains make are not mistakes at all, but natural outcomes of a mathematical process that, while imperfect, is extraordinarily effective at making sense of a complex and ever-changing world. Uncomputable numbers are a mind-bending concept in mathematics, revealing that there are numbers whose existence we can prove, yet no algorithm can ever calculate them in full detail. To start, it helps to understand what it means for a number to be computable. A computable number is one for which there exists an algorithm, a finite, step-by-step procedure, that, given any natural number n, can produce the nth digit of that number. This idea stems from computer science and mathematical logic, where mathematicians and pioneers like Alan Turing developed the theory of computation. For instance, pi and e are computable because we have explicit formulas and algorithms that generate their infinite decimal expansions, no matter how far we wish to go. In stark contrast, an uncomputable number is one for which no such algorithm exists. Even though we know these numbers exist, there is no systematic procedure that can list out their digits one by one to any desired degree of accuracy. The proof of the existence of uncomputable numbers is a brilliant application of mathematical logic and set theory. Turing's work on the halting problem, for example, showed that there is no general algorithm that can determine whether any given computer program will eventually stop running or run indefinitely. This result implies that the set of all programs, or more formally, the set of all algorithms, is countable, meaning they can be listed one after another. However, the set of all real numbers is uncountably infinite, as proven by Cantor's diagonal argument. Since there are many more real numbers than there are algorithms to compute them, almost every real number is uncomputable. In other words, while computable numbers form a tiny, special subset of the continuum, uncomputable numbers dominate the number line, even though we rarely come across them in practical calculations. A famous example of an uncomputable number is Chaitin's constant, often denoted by omega. This number represents the probability that a randomly generated program will eventually halt. While it is rigorously defined through the lens of algorithmic information theory, it turns out that no algorithm can compute its digits. In essence, omega encodes in its infinite string of digits answers to deep questions about the limits of computation. But by its very nature, it resists any attempt to be fully calculated or even approximated beyond a certain point. The unpredictability of omega's digits is not due to any randomness per se, but rather to the inherent limitations imposed by the theory of computation. The implications of uncomputable numbers are profound. They remind us that even in the seemingly precise and deterministic world of mathematics, there exist limits to what can be known or computed. While we might strive to find patterns and formulas to describe every number, uncomputable numbers serve as a counterbalance, illustrating that there is more to the mathematical universe than what can be algorithmically generated. This revelation shatters the notion that all mathematical truths are accessible through computation, underlining a fundamental gap between what exists and what can be effectively calculated. Philosophically, uncomputable numbers challenge our view of mathematical existence. They belong to the realm of abstract objects that are proven to exist by non-constructive methods. In other words, we can demonstrate that these numbers must be there by understanding the structure and cardinality of the real numbers, even though we can never see them through computation. This idea resonates with broader themes in mathematics and philosophy about the nature of infinity and the limits of human knowledge. It forces us to accept that some truths are inherently beyond our computational reach, not because of practical limitations like time or memory, but due to the very nature of logic and computation. Moreover, the concept of uncomputable numbers has significant ramifications for fields such as cryptography, complexity theory, and even theoretical physics. In cryptography, for example, the idea that certain numerical problems cannot be solved by any algorithm underpins the security of many encryption systems. In complexity theory, uncomputability provides a rigorous way of understanding the boundaries of what computers can do. And in physics, uncomputability raises fascinating questions about the limits of predicting the behavior of complex systems, potentially even influencing our understanding of phenomena in quantum mechanics. In summary, uncomputable numbers stand as a testament to the intrinsic limitations of computation amidst the vast landscape of mathematical existence. They are numbers whose existence is incontrovertibly established by elegant proofs and logical reasoning, yet they elude the grasp of any algorithmic process. This dichotomy between existence and computability not only enriches our understanding of mathematics, but also humbly reminds us that our computational methods, however powerful, are bounded by deep and beautiful principles governing the nature of infinity and information. The study of uncomputable numbers is a vivid illustration of how randomness, structure, and the abstract realms of logic converge, showing us that even in the world of numbers, there are mysteries that forever lie just beyond the reach of calculation. Arrow's impossibility theorem stands as one of the most startling results in social choice theory, demonstrating that no voting system can perfectly capture the fairness we instinctively expect in a democratic process. At its core, the theorem addresses the fundamental challenge of converting diverse individual preferences into a single collective decision, a task that seems simple at first glance, but grows increasingly complex when you demand that the decision process meets a set of reasonable, fair criteria. Arrow identified several conditions that a perfect voting system should satisfy. These include the idea that if every voter prefers one alternative over another, then the group ranking should reflect that unanimity, a condition known as Pareto efficiency. It also requires that the method of aggregating preferences should be independent of irrelevant alternatives. That is, the group's decision between any two options should depend only on the individual voter's preferences between those two, not on other extraneous candidates or issues. Furthermore, a democratic system must be non-dictatorial, meaning that no single individual's preferences should always dictate the outcome regardless of the opinions of all other voters. What Arrow's theorem rigorously proves is that when there are at least 3 distinct alternatives, it is impossible to design a voting system that simultaneously satisfies all these fairness criteria. The implications are profound. Every voting method must compromise on at least one of these principles. In essence, if you insist on having a system that treats all options with a certain level of fairness and respects the diversity of opinions, then you must accept that there will be situations where the group decision can seem arbitrary or even paradoxical. This realization has shaken the foundations of democratic theory because it mathematically confirms that no method of aggregating individual preferences can be completely immune to producing outcomes that seem at odds with our intuitions about fairness. To illustrate, imagine a scenario with 3 candidates, A, B, and C, and a diverse electorate whose preferences vary widely. A voting system that guarantees every voter's preference is considered might still lead to an outcome where the collective ranking violates the independence of irrelevant alternatives. In such a case, the introduction or removal of a less popular candidate could unexpectedly alter the relative order of the remaining candidates, exposing a vulnerability in the system. Alternatively, if the system is tweaked to avoid that problem, it might inadvertently give one voter disproportionate power, rendering the decision effectively dictatorial. This tension is at the heart of Arrow's result. Democracy, when formalized and analyzed mathematically, is forced to confront the fact that no perfect system exists, and every method carries inherent trade-offs. The theorem does not imply that democratic decision-making is useless, but rather that perfection is unattainable. Instead, it provides critical insights into the compromises inherent in any voting process. By highlighting these unavoidable limitations, Arrow's work encourages us to think carefully about the values we prioritize in a voting system. Should we favor a system that is more resistant to strategic manipulation at the cost of occasionally ignoring some voter preferences? Or should we prioritize a method that nearly always respects unanimous agreements, even if it sometimes allows external factors to sway the outcome? Each approach embodies a different set of compromises and trade-offs, and Arrow's theorem serves as a mathematical reminder that there is no silver bullet. There is no ideal system that can sidestep these fundamental issues. In broader terms, the significance of Arrow's impossibility theorem extends far beyond electoral politics. It challenges us to reflect on the inherent conflicts that arise when trying to reconcile individual freedoms with collective decision-making. The theorem forces us to acknowledge a critical truth about democracy. The principles of fairness, unanimity, and independence, while deeply desirable, cannot all coexist perfectly within a single framework. This realization invites deeper philosophical questions about the nature of fairness and the limits of rational decision-making within society. Rather than discrediting democracy, Arrow's result emphasizes the importance of continual dialogue, thoughtful compromise, and the recognition that all systems, no matter how well designed, are subject to inherent limitations. Ultimately, Arrow's impossibility theorem is a testament to the power of mathematical reasoning in uncovering the hidden complexities of social processes. It reveals that even the most cherished ideals of democratic fairness are bound by the constraints of logic, providing a humbling perspective on our attempts to engineer a flawless collective decision-making process. In the end, while democracy may never achieve a state of perfect fairness, understanding these mathematical limitations helps us build more informed, resilient, and adaptable systems that strive to balance the diverse interests of all citizens as fairly as possible, even if perfection remains forever out of reach. The Grue and Bleen paradox is a thought-provoking challenge to our understanding of color, and by extension, to the way mathematics and logic attempt to define and predict properties in the world. To begin, let's consider what we mean by color. In everyday language, we use words like green or blue to describe the colors of objects. But the paradox, introduced by philosopher Nelson Goodman in the mid-20th century, asks us to reflect on how these definitions can be so fluid that even mathematics and logic, which thrive on precision, struggle to capture their true nature. Imagine that we define a new predicate, Grue. Under this definition, an object is called Grue if it is observed before a certain arbitrary time t and is green, or if it is observed after time t and is blue. Similarly, we can define Bleen such that an object is Bleen if it is blue when observed before time t, or green when observed after time t. Notice that until the cutoff time t, all objects that are green are also Grue, and all objects that are blue are also Bleen. The twist emerges after time t. When we see an emerald that is still green, our conventional intuition tells us it remains green, but according to our Grue definition, it should be blue if observed after t. This peculiar construction forces us to question what it means for a predicate to be projectable or reliable for making predictions. In the realm of mathematics and logic, we like definitions to be stable and context-independent, so that evidence gathered before a certain time can reliably predict the future. However, if we adopt the Grue-Bleen scheme, then the same evidence used to confirm that all emeralds are green would equally confirm that all emeralds are Grue. Yet these two statements, while identical in their predictions prior to time t, lead to dramatically different expectations about what we will observe after time t. This is where the paradox reveals its force. Our logical and mathematical frameworks, which rely on clear, non-arbitrary predicates, seem to buck under the weight of definitions that incorporate time as an intrinsic part of the predicate. The problem here is not merely one of semantics or linguistic quibbling. It touches on the heart of inductive reasoning. Induction is a method we use to generalize from observed cases to unobserved ones. We see 1,000 emeralds as green, and we naturally predict that the next emerald will also be green. But when we introduce Grue, we have created a situation where our inductive inference can be split. The same observed evidence can equally support that all emeralds are green or that all emeralds are Grue. Since these two predictions diverge after time t, our simple inductive reasoning appears to break down. This forces mathematicians and logicians to confront a crucial question. what constitutes a natural or projectable property, and if the notion of color is as susceptible to arbitrary redefinition as Grue and Bleen, can mathematics ever truly pin down such subjective qualities? Many have argued that the solution lies not in refining our logical tools, but in recognizing that some predicates, like green or blue, are more natural because they are rooted in the way our perceptual systems have evolved to process information about the environment. These color terms are intrinsically linked to the physical properties of light and to the human visual system, and they tend to have a stability that the artificial predicates Grue and Bleen lack. In other words, green is a concept that has developed over time and through shared experience, becoming a projectable quality because it corresponds to a consistent feature of the world. Mathematics and logic, then, are not so much at fault as they are highlighting the tension between the rigor of formal definitions and the messy, evolving nature of everyday language and perception. At its core, the Grue and Bleen paradox exposes a limitation of formal systems. While mathematics strives for precision and universality, the concepts it seeks to define can be deeply influenced by the context, history, and even the temporal perspective of human observers. The paradox challenges us to consider that some ideas might forever elude a neat, all-encompassing definition. Instead of a failure of logic, it may be more accurate to view the paradox as a reminder that the world is richer and more variegated than our models sometimes allow. Furthermore, this thought experiment has broader implications beyond the philosophy of color. It touches on issues of confirmation and the reliability of inductive inference in science as a whole. In many scientific contexts, the predicates we use to describe phenomena are chosen because they are natural and robust over time. The Grue-Bleen dilemma forces us to ask whether our categorizations reflect inherent qualities of the natural world, or whether they are, at least partly, constructs of our conceptual framework. In doing so, it blurs the line between objective reality and subjective interpretation, a challenge that mathematics and logic must continuously grapple with, especially when applied to the human experience. In summary, the Grue and Bleen paradox illustrates why mathematics and logic sometimes struggle to define concepts like color. It reveals that our classifications are not purely objective, but instead are influenced by context, time, and human perception. While formal systems aim for clarity and consistency, the fluid nature of terms like green exposes the limitations of these systems when they confront the ever-changing landscape of real-world experience. The paradox is a powerful reminder that even with our rigorous tools, some aspects of reality, especially those tied to our sensory and cognitive faculties, resist neat encapsulation and defy absolute definition. The Burali-Forti Paradox reveals one of the most astonishing insights of set theory by demonstrating that the idea of a largest number, or more precisely, a largest ordinal, leads to a logical contradiction. To appreciate this paradox, we must first understand what ordinal numbers are and how they function in mathematics. Ordinals extend the concept of natural numbers to describe the order type of well-ordered sets, providing a way to not only count elements, but also to compare their sizes in terms of order. In our everyday experience, there is no largest natural number because for any number you choose, adding one gives a larger number. However, when we try to collect all ordinal numbers together into one set, our intuitions about size and order break down. Imagine trying to construct the set of all ordinal numbers, which are defined by their property of being well ordered by the membership relation. Each ordinal represents a position in a sequence that goes on without end, like the natural numbers. Yet there are also infinite ordinals that capture different orders of infinity. If we assume that the collection of all ordinals forms a set, then by the very nature of ordinals, this set must itself have an ordinal number, the ordinal that represents its order type. In other words, if you take all these ordinals and line them up in order, there should be a last element, the largest ordinal. But here lies the contradiction. If this largest ordinal exists, it must, by the rules of ordinal arithmetic, be greater than every ordinal that comes before it. Yet, since it is constructed from all ordinals, it must also be included among those ordinals. That means it would have to be strictly greater than itself, a logical impossibility. This contradiction shows that the collection of all ordinal numbers cannot form a set as we normally understand it. Instead, it must be considered a proper class, a collection too large to be a set without leading to inconsistencies in our mathematical framework. The significance of the Burali-Forti Paradox extends well beyond a curiosity about the largest number. Its discovery forced mathematicians to refine the foundations of set theory, leading to the development of axiomatic systems that differentiate between sets and proper classes. Such a distinction is crucial. While sets are well-behaved collections that we can manipulate using standard set theoretic operations, proper classes are so vast that treating them as sets would allow paradoxes like Burali-Forti to arise. This realization laid the groundwork for modern theories that ensure consistency within mathematics by careful formulation of what can and cannot be considered a set. Historically, this paradox, first identified by Cesare Burali-Forti in the late 19th century, sent shockwaves through the mathematical community. It challenged the prevailing assumptions about infinity and highlighted the necessity of rigorous logical foundations. The idea that there could be different sizes or types of infinity was, and remains, a profound insight that reshaped how mathematicians view the infinite. The paradox not only shows that some infinities are larger than others, a concept that can seem almost mystical, but also that our intuitive grasp of quantity and order must be re-examined when dealing with the infinite. Moreover, the Burali-Forti Paradox provides a clear example of how seemingly simple concepts, when extended to their logical extremes, can lead to contradictions if not properly constrained. It illustrates that the notions of largest or complete collections, which work fine in finite contexts, become problematic and even impossible when applied to the infinite. In the realm of infinite sets and ordinal numbers, our familiar arithmetic rules are no longer sufficient. They must be adapted to account for the extraordinary properties of infinite collections. In the broader context of mathematics, this paradox influences various areas, from the study of ordinal and cardinal numbers to the formulation of consistent set theories such as Zermelo-Fraenkel set theory with the axiom of choice, ZFC. By revealing inherent limitations in our naive approach to infinity, the Burali-Forti Paradox has become a central point of discussion in philosophical debates about mathematics and the nature of infinity itself. It serves as a reminder that even the most fundamental concepts, like numbers and order, have layers of complexity that challenge our understanding. Ultimately, the Burali-Forti Paradox underscores the delicate balance that mathematics must maintain between intuition and rigor. The notion of a largest number is not merely about finding an endpoint in a list. It is a gateway to deep questions about the structure of mathematical reality. Through the paradox, we learn that the infinite is not a uniform, monolithic concept, but a landscape filled with surprising intricacies and unexpected challenges. Mathematics, by confronting and resolving such paradoxes, continues to evolve, deepening our understanding of not only numbers, but the very nature of logical reasoning and truth. The paradox of the heap, also known as the Collatz Paradox, challenges us to mathematically define the vague boundary between a collection of individual grains of sand and what we call a heap. At first glance, the problem seems almost trivial. One grain of sand is clearly not a heap, and if you add one grain at a time, at some point, you must have a heap. Yet, when you try to pinpoint the exact moment the transition occurs, you quickly run into trouble because each addition seems insignificant on its own. There is no precise moment when non-heap definitively becomes heap, and this ambiguity forces us to confront the limits of strict definitions in mathematics and logic. To start, consider a single grain of sand. Intuitively, one grain does not constitute a heap. If you add another grain, you still do not have a heap. But if you continue to add grains, at some point, you would say, "Now that is a heap." The paradox arises because our language and concepts, terms like heap, are inherently vague. Each time you add one grain, the change is so slight that it never seems sufficient to alter the overall classification. Yet, if you add enough grains, the cumulative effect is undeniable. This gradual and incremental change is what makes the paradox so perplexing. There is no clear, mathematical threshold that divides a heap from a non-heap. Mathematically, this problem touches on the notion of predicates that lack sharp boundaries. Traditional logic expects that every predicate should either be true or false when applied to an object. In the case of heap, however, the boundary is fuzzy. One way mathematicians have attempted to address such vagueness is through the use of fuzzy logic. Unlike classical binary logic, fuzzy logic allows for degrees of truth. Instead of saying an object is either a heap, true, or not a heap, false, we can assign a value between 0 and 1 that indicates the degree to which the collection of grains qualifies as a heap. For example, a small pile might be assigned a value of 0.2, while a large pile might be 0.9, with the transition between non-heap and heap occurring gradually rather than abruptly. This method mirrors our intuitive understanding better by acknowledging that natural language often admits shades of meaning instead of absolute categories. Another mathematical approach involves setting a threshold based on some contextual or practical criteria. In everyday contexts, we might decide that once the number of grains exceeds, say, 10,000, the collection is large enough to be considered a heap. However, such a threshold is arbitrary. It works for practical purposes or for certain applications, but it does not resolve the fundamental issue. Why 10,000 and not 9,999? The lack of an intrinsic, objective cutoff point is at the heart of the paradox. The problem illustrates that many concepts, especially those rooted in human perception, resist neat encapsulation by rigid mathematical boundaries. The paradox of the heap also highlights interesting connections to other philosophical and mathematical issues, such as the problems of vague boundaries in other predicates. Terms like bald or tall face similar difficulties. In each of these cases, there is a gradual transition where no clear point of change can be discerned. Mathematicians and philosophers have used these paradoxes to debate the nature of induction and to question whether classical logic can fully account for the nuances of natural language and experience. Furthermore, This paradox invites us to consider the limitations of mathematical models when applied to real-world phenomena. While mathematics excels at providing clear-cut definitions and precise boundaries in many areas, the natural world, and indeed many concepts we use to describe it, often does not conform to such strict divisions. Instead, nature seems to operate on continua where transitions are smooth and ambiguous. The paradox of the heap is a vivid reminder that while mathematical abstraction is immensely powerful, it sometimes struggles to capture the messy and gradual transitions that occur in reality. In practical fields, such as computer science or decision theory, acknowledging the fuzziness inherent in concepts like heap can lead to more robust models. For example, when designing algorithms for image recognition, engineers often use methods that account for uncertain or partial membership in a category, rather than forcing an all-or-nothing classification. This approach is directly inspired by the need to grapple with paradoxes similar to the Sorites, where the goal is not to pinpoint an exact threshold, but to work with a continuum of possibilities. Ultimately, the paradox of the heap serves as both a philosophical conundrum and a practical lesson. It shows that our everyday language and intuitive classifications might work well for routine purposes, but they conceal deep complexities when scrutinized through the lens of rigorous logic and mathematics. The paradox challenges us to embrace a more flexible, nuanced way of thinking, a perspective that appreciates both the power and the limitations of mathematical definitions when applied to the fluid, gradational nature of the real world. In summary, while mathematics strives for precision and clear boundaries, the paradox of the heap reveals the inherent difficulty in defining concepts that are fundamentally vague. It underscores that some ideas, like the transformation of individual grains of sand into a heap, elude exact mathematical characterization. Instead, they invite approaches like fuzzy logic and contextual definitions, reminding us that reality often lies on a spectrum. This challenge not only deepens our understanding of language and logic, but also enriches our appreciation for the intricate, often ambiguous nature of the world we seek to describe. Quantum immortality is a provocative thought experiment that arises from the interplay between quantum mechanics and probability theory, particularly when viewed through the lens of the many worlds interpretation. At its core, the concept explores the possibility that, at every quantum event with multiple possible outcomes, especially those involving life and death, our reality branches into numerous parallel worlds. In each branch, a different outcome occurs, so that in some branches, the observer survives even when the odds are extremely low. This idea forces us to reconsider what it means to die, and how probability works when we extend our analysis to the infinite tapestry of quantum possibilities. Mathematically, quantum events are governed by probabilities. In a typical scenario, suppose there is a survival event with probability p, where 0 is less than p is less than 1, during a dangerous experiment. Under classical probability, if the experiment is repeated n times, the chance of surviving every trial is p to the power of n, which tends towards 0 as n grows large. Intuitively, this tells us that, given enough trials, survival should become nearly impossible. However, the many worlds interpretation suggests a different picture. Instead of a single linear sequence of events where every trial's outcome is independent and only one possibility is realized, every possibility with non-zero probability is actualized in some branch of reality. Consequently, while the measure, the overall weight of probability of survival branches, may be exceedingly small, when aggregated, the subjective experience of an individual is confined to those branches in which they do not encounter death. This raises a paradoxical notion. From a first-person perspective, an individual might never experience their own death, because in every experiment where a quantum event determines survival, there will always be at least one branch in which they continue living. In this sense, the conscious observer self-selects for continuous survival, regardless of how improbable that survival might appear when viewed from the outside. Mathematically, while the external, global probability for continued life across an infinite sequence of events appears to vanish, since Pn, 0 as n infinity, the subjective experience is only ever associated with the branches where survival occurs. In these surviving branches, even if they are of infinitesimally small measure, the observer's experience persists. Critics of quantum immortality point out several complications. For one, if the overwhelming majority of branches lead to a catastrophic end, then even the branches that ensure survival may be characterized by extreme suffering or degraded quality of life. The mathematics of infinite branching does not necessarily guarantee a desirable form of immortality, but rather it posits the formal possibility that conscious experience persists indefinitely in at least one branch. Furthermore, the very notion of measure in the many worlds interpretation is subtle. While every outcome with non-zero probability is realized, some branches might contribute so little to the overall measure that they are, from a practical standpoint, negligible, even if subjectively an individual finds themselves in one of those rare branches. The challenge of reconciling these ideas mathematically compels us to re-examine the foundations of probability theory when applied to quantum events. Traditional approaches treat probabilities as relative frequencies measured over many trials. Yet, in an infinite multiverse, the observer's path is not a simple matter of accumulating failures. It is instead a path that necessarily follows the branch of survival at every decision point. This leads to an unconventional perspective where, although the probability of survival diminishes to nearly zero from an external viewpoint, the subjective I always finds itself in the outcome where it continues to exist. In effect, quantum mechanics and the mathematics of probability combine to produce a scenario where the future of the observer is split into an infinite number of possibilities, and survival, even if statistically improbable in each instance, becomes a certainty along at least one branch. Ultimately, quantum immortality forces us to confront how we understand both probability and the nature of existence itself. Mathematically, it challenges conventional interpretations by suggesting that the laws governing quantum events, when applied over an infinite horizon, could allow for a kind of immortality that defies our everyday expectations. The theoretical framework does not claim that one can expect a comfortable or even sane eternal life, merely that death, as experienced subjectively, might be sidestepped in a universe where every possibility unfolds. This idea remains highly controversial and speculative, and its implications have sparked lively debate among physicists, philosophers, and mathematicians alike. In summary, quantum immortality is an exploration of the infinite survival scenarios that arise when quantum events cause branching realities. While classical probability suggests that survival becomes nearly impossible over a long series of risky events, the many worlds interpretation and its attendant mathematical models implies that there is always some branch where consciousness persists indefinitely. This extraordinary idea reshapes our understanding of life, death, and the probabilities that govern the universe, illustrating the subtle interplay between quantum mechanics and our subjective experience of reality. The Doomsday Argument is a controversial, probabilistic argument that attempts to forecast the likely remaining duration of human existence by employing principles from probability theory and Bayesian reasoning. The idea begins with the observation that, as individuals, we should consider ourselves randomly selected from the entire set of humans who will ever live. If we assume that we are typical, then our birth rank, or our position in the overall sequence of human births, provides a statistical clue about the total number of humans that will ever come into existence. For instance, if you estimate that roughly 100 billion humans have been born up to now, and you consider yourself somewhere in that middle rank, then a simple probabilistic reasoning suggests that it would be surprisingly unlikely for the total human population to be several orders of magnitude larger, as that would imply that you were born very early in a vastly long series. In other words, if humanity were to persist for many more millennia, with trillions more individuals coming into being, it would be statistically unlikely to find oneself among the early generations. The argument employs what is known as the self-sampling assumption. This is the idea that you should reason as if you are a random sample from the set of all human beings, past, present, and future. Under this assumption, your birth order acts as a kind of data point. For example, if you rank yourself roughly in the first 100 billion of an unknown total population, then under the assumption of typicality, it becomes unlikely that the total number of humans will be, say, 10,000 billion. In Bayesian terms, one updates their belief about the total number of humans, given the data point that you find yourself relatively early in the distribution. In many formulations of the argument, this updating leads to the conclusion that the likelihood is higher that the total number of humans will not be vastly larger than the number already born, implying that humanity might reach its end much sooner than if we assumed an endlessly growing future. Critics of the Doomsday Argument raise several key objections. One common criticism is that the self-sampling assumption may be flawed. Critics argue that our observational position might not be as random as assumed because our existence could be conditional on various factors that are not accounted for in the simple, probabilistic model. Others point out that the argument seems to sidestep the complexities associated with technological and social evolution. For example, advances in medical technology, space exploration, and artificial intelligence could dramatically alter the pattern of human births and longevity, making it difficult to apply a static statistical model to such a dynamic process. Moreover, some find the argument psychologically unsettling, as it forces us to confront the possibility that the odds of our own extinction might be higher than our intuition would suggest. Another layer of complexity comes from the distinction between different types of probability measures. While some formulations of the Doomsday Argument use a frequentist perspective, others invoke Bayesian inference, which depends on one's choice of prior probability distributions. The conclusions can differ dramatically depending on these priors, and there remains no consensus among proponents on how best to choose them. This sensitivity to initial assumptions means that the argument is, to some extent, a reflection of subjective Bayesian reasoning rather than an objectively inescapable conclusion drawn solely from the data. It's not that the mathematics necessarily predicts imminent extinction. Rather, when its assumptions are taken at face value. The probabilistic reasoning suggests that the future human population is unlikely to be much larger than what we have already seen. Despite the controversies, the Doomsday Argument has had a significant influence on discussions about existential risks and long-term survival strategies. It pushes us to examine how we update our beliefs about global catastrophic risks based solely on our current place in history. By highlighting that the mere fact of our relatively early existence could be indicative of a truncated future, the argument serves as a cautionary reminder to carefully consider the threats facing humanity, from environmental collapse to technological hazards, while also probing the philosophical and epistemological limits of our predictive models. In summary, the Doomsday Argument leverages mathematical reasoning about probability and the concept of typicality to argue that our relatively early position in the sequence of all human births may imply a higher likelihood of an earlier end for humanity than one might otherwise assume. While the argument is far from universally accepted and remains deeply controversial due to its reliance on specific assumptions about randomness, sampling, and priors, it provides a fascinating example of how mathematics can be applied to macro-level questions of survival and extinction. The discussion it ignites about the nature of existence, the reliability of our statistical inferences, and the implications for policy and global planning ensures that, whether or not one accepts its conclusions, the Doomsday Argument will remain a thought-provoking and influential line of inquiry in existential risk studies. The mathematics of music and emotions is an extraordinary demonstration of how numerical patterns and abstract relationships manifest into art that resonates deeply within us. At its essence, music is constructed upon a foundation of sound frequencies and time intervals, and it is these mathematical relationships, such as ratios, harmonics, and symmetry, that give music its structure and, ultimately, its emotional impact. Consider the harmonic series, where naturally occurring overtones create frequency ratios, like 2:1 for octaves or 3:2 for perfect fifths. These simple ratios are not only fundamental to musical tuning, but also to the reason our ears perceive certain combinations of notes as pleasingly consonant. Our perception of these intervals is shaped by biology and evolution, making them nearly universal across diverse cultures. Delving deeper, the construction of musical scales further demonstrates the interplay between mathematics and emotion. The widely used 12-tone equal temperament system divides the octave logarithmically into 12 equal parts, ensuring that the ratio between adjacent notes remains constant. This division is mathematically elegant and, at the same time, provides musicians with the flexibility to transpose music into any key while preserving harmonic relationships. Such mathematical precision creates a balance in the sound that our auditory system subconsciously recognizes as harmonious. When we hear music that adheres to these balanced ratios, our brains are triggered into a state of recognition and comfort, evoking emotions ranging from joy to tranquility. Rhythm and timing are equally essential elements where mathematics plays a critical role in evoking emotion. Many composers leverage rhythmic patterns that align with mathematical sequences or proportions, such as the Fibonacci series or the golden ratio, to craft passages that feel naturally progressive and balanced. These patterns can regulate the dynamics of tension and release in music. For example, a piece might build up suspense through a gradually increasing tempo or syncopation, a manipulation of time that creates an unexpected twist before resolving into a familiar, stable rhythm. This temporal modulation, governed by mathematical relationships, mirrors processes found in nature and creates an emotional narrative within the music, guiding the listener through waves of anticipation, climax, and resolution. The use of symmetry and symmetry breaking in music further exemplifies the connection between mathematics and emotion. Symmetry in musical phrases provides a sense of order and predictability that can be deeply satisfying to the human mind. However, slight deviations from perfect symmetry, intentional variations introduced by composers, can add surprise and interest to a composition. This delicate balance between order and disorder is central to our emotional response. Too much order can become monotonous, while a complete lack of structure can feel chaotic. The emotional impact arises precisely because our brains appreciate a pattern that is intelligible, yet vibrant enough to leave room for creative unpredictability. Such is the art of composition, where mathematical principles allow for both precision and creative freedom. Moreover, the mathematics of music is not confined to pitch and rhythm alone. It also extends into the realm of dynamics and timbre. The way sound evolves over time, its amplitude, attack, and decay is governed by exponential functions and differential equations. When these sound patterns are layered and intertwined, they give rise to rich textures and complex soundscapes that can evoke a wide range of emotions, from the stark loneliness of a single instrument in a vast hall to the overwhelming euphoria of a full orchestral crescendo. Our auditory system is exquisitely sensitive to these changes, processing the dynamics through neural mechanisms that translate mathematical variations in sound into the language of feeling. Yet, perhaps the most profound aspect of the relationship between mathematics, music, and emotion lies in the concept of emergence. Emergence refers to the phenomenon where simple underlying rules give rise to complex, unpredictable, and aesthetically pleasing behaviors. In the realm of music, the simple harmonic ratios and rhythmic patterns combine in non-linear ways to produce compositions that are far more than just the sum of their parts. This emergent complexity is analogous to fractals in mathematics, patterns that, despite being generated by simple iterative processes, reveal endless intricacy upon closer examination. Just as fractals capture our imagination with their infinite detail, music created on the foundation of simple mathematical truths can evoke deep emotional responses that are both surprising and profoundly moving. Finally, the emotional resonance of music, as rooted in mathematical structure, speaks to the universality of human experience. The fact that mathematical relationships underpin the principles of musical harmony, rhythm, and dynamics suggests that there is an objective basis for why certain sounds touch us so deeply. Regardless of cultural background, many people respond similarly to the harmonic and rhythmic patterns that have been discovered and refined over centuries. Mathematics, with its universal language, helps explain this phenomenon, demonstrating that the patterns we find in nature are not arbitrary, but are echoed in the art we create and the feelings we experience. In conclusion, the mathematics of music and emotions is a testament to the power of numerical relationships to shape our inner lives. From the clear consonance of harmonic intervals to the intricate dance of rhythm and symmetry, mathematical principles provide the scaffolding upon which music is built. It is through these structures that music communicates not just a series of sounds, but a spectrum of human emotions. The interplay between determinism and creativity, order and spontaneity, encapsulated in mathematical ratios and patterns, ultimately reveals why certain compositions resonate on a universal level, touching the depths of human sentiment while delighting the mind with their inherent logic and beauty. Braess Paradox: how adding roads can mathematically worsen traffic. This counterintuitive phenomenon challenges the common sense expectation that building more roads will naturally ease congestion and improve traffic flow. Instead, under certain conditions, adding extra routes to a transportation network can lead to a new equilibrium in which every driver experiences longer travel times. Imagine a simplified road network where commuters have two distinct routes to travel from their starting point to their destination. Each route has different segments with travel times that depend on the number of vehicles using them. In the original configuration, drivers distribute themselves among the available routes in a way that minimizes their own travel time, a situation that aligns with what mathematicians and economists call a Nash equilibrium. At this equilibrium, no single driver can reduce their travel time by unilaterally switching to a different route. Surprisingly, however, when a new road is introduced into this network, one that appears to offer a shortcut or more efficient path, the overall behavior of drivers changes. Because every commuter acts in self-interest, many will opt to use the new road, expecting to shave off minutes from their journey. The catch is that, as more drivers make this seemingly beneficial switch, the new road becomes heavily congested. The additional traffic not only slows down the new connection, but also disrupts the balance among the original routes. When drivers continuously adjust their choices to minimize their personal travel time, the network settles into a new Nash equilibrium. In many instances described by Braess Paradox, this new equilibrium turns out to be less efficient overall. That is, even though an additional road was added, each individual ends up with a longer travel time compared to the scenario before the extra road was built. Mathematically, this paradox is explained using the concept of self-interested routing. Each driver is modeled as a rational agent seeking to minimize their own cost, or travel time, without consideration for the cumulative effect of their choice on the system. In the pre-paradox network, the travel times on the routes are determined by the sum of the independent contributions from each road segment. When an extra connection is added, it alters the relationships between these segments. The new road provides an alternative path that disrupts the previously optimal balance. Through the lens of game theory, the system's equilibrium shifts when each driver's decision, made independently, results in a globally suboptimal outcome. This is reminiscent of the tragedy of the commons, where individual rational action leads to collective inefficiency. A classic illustration of Braess Paradox involves a network where two main routes connect a starting point, A, and a destination, B. Suppose one route is characterized by a travel time that increases linearly with the number of cars, while the other route has a fixed travel time regardless of traffic. Initially, drivers split across these routes to optimize travel times. Now, imagine adding a direct road connecting intermediate points on these routes, a seemingly advantageous shortcut. Initially, drivers perceive that this connection may reduce travel time. However, as more drivers funnel into the shortcut, congestion builds up not only on the new link, but in adjacent segments as well. The overall travel time increases for everyone. The paradox mathematically demonstrates that under the assumption of selfish routing, the addition of extra capacity does not necessarily translate to improved flow. In fact, it can interfere with established equilibria in unpredictable and detrimental ways. Beyond theoretical interest, Braess Paradox has practical implications in transportation planning and urban design. In several real-world cases, traffic engineers and city planners observed that removing certain roads or limiting access to highways, actions that on the surface seem counterproductive, can actually improve traffic flow. These instances echo the paradox's message. Sometimes less is more. By intentionally restricting available routes, the network can achieve an equilibrium state that is more efficient overall, reducing congestion and improving travel times for all users. Furthermore, Braess Paradox isn't confined solely to road networks. Its principles have been extended to other areas, such as internet routing, where additional pathways can sometimes lead to data bottlenecks, and even in power grids and networked systems, where adding extra connections might redistribute loads in unforeseen ways. In each instance, the underlying mathematics reveals that when individual agents or pieces of a system optimize locally without considering the global picture, the result can be a less than ideal collective outcome. In summary, Braess Paradox offers a profound mathematical insight into complex systems and the nature of equilibrium under self-interested behavior. It demonstrates that the intuitive solution of adding more capacity can backfire if it disrupts a delicate balance, leading to increased congestion and slower travel times for everyone. By challenging our assumptions about optimization and efficiency, the paradox not only enriches our theoretical understanding of network dynamics, but also serves as a practical guide for designing systems, from highways to digital networks, that are robust, efficient, and ultimately better for society. Mathematical Illusions of Certainty explores how numbers and mathematical models, while offering a structured view of the world, can create the illusion that we have complete control over uncertainty. In everyday life, we routinely encounter statistics, formulas, graphs, and probabilities that suggest the existence of underlying order amid apparent randomness. This sense of order instills confidence, giving us the impression that by engaging with numbers, we can predict, manipulate, and ultimately master the unpredictable elements of life. Yet, beneath this veneer of control lies a paradox. While mathematics quantifies uncertainty, it does not eliminate it, and our reliance on these numerical frameworks can sometimes lead us to overestimate our grasp on reality. At its core, mathematics is a language of patterns and relationships. Whether it's the probability theory that explains coin tosses or the statistical models used to forecast weather, numbers allow us to condense complex random phenomena into digestible information. For instance, when meteorologists predict a 70% chance of rain, they present a degree of certainty about future events. To the layperson, this probability feels like a concrete forecast, a measure of control over the whims of nature. However, these figures are derived from models that incorporate an array of assumptions, simplifications, and approximations. The inherent randomness of natural systems means that despite the precision of the numbers, certainty remains an illusion. Rather than controlling uncertainty, mathematics provides a tool to navigate it, offering guidance while acknowledging that outcomes can still diverge from predictions. The illusion of certainty is further cemented by the very act of measuring and quantifying phenomena. In scientific research and everyday decision-making alike, numbers give the appearance of precision. Consider how economists use predictive models based on historical data to forecast future market trends. These models often come with impressively exact numbers and percentages that suggest a deterministic outcome. Yet even the most sophisticated models can only capture a slice of reality. Factors such as human behavior, unforeseen events, and complex interactions between variables mean that the real world often defies perfect prediction. The confidence we place in these numerical predictions, despite their underlying uncertainties, illustrates how mathematics can lull us into believing that uncertainty is something that can be tamed by sheer computation. Moreover, human cognition is particularly predisposed to appreciate clarity and precision. Numbers, with their crisp lines and exact figures, are psychologically persuasive. When we see a statistic or a well-organized chart, we feel reassured that we have a rational understanding of a situation. This is why, for example, in fields ranging from medicine to finance, metrics and performance indicators are often taken as definitive guides for action. The phenomenon is not merely about data, it taps into our desire for control in an inherently unpredictable universe. By translating randomness into percentages and ratios, mathematics offers a form of comfort, a belief that even the chaotic can be distilled into order. Yet, this comfort comes at a cost. The illusion of certainty can lead to overconfidence and, at times, to decision-making that underestimates risk. In legal or policy decisions, for example, an over-reliance on statistical evidence can result in the dismissal of factors that are difficult to quantify, such as social dynamics or moral considerations. Similarly, in the realm of finance, complex quantitative models have sometimes given investors a false sense of security, contributing to decisions that precipitate economic crises when the uncertainties these models overlook come to bear. In each case, the precision of numbers masks the underlying ambiguities, blurring the line between what is known and what is merely assumed. One striking example of the mathematical illusion of certainty lies in the interpretation of p-values in scientific research. A p-value is used to determine the statistical significance of experimental results, often leading researchers to conclude that certain effects are real or causal based solely on a threshold of 0.05. However, this use of a rigid numerical cutoff disguises the nuance inherent in experimental data. Even a p-value just below 0.05 does not guarantee that an observed effect is both reproducible and practically significant. And yet, the straightforward appearance of this number can give researchers, and those who read about their results, the unfounded impression that scientific experiments provide clear-cut, unquestionable evidence, thereby reinforcing the illusion of complete mathematical certainty. Furthermore, the illusion is compounded by the simplifications inherent in our mathematical models. Whether they describe climate patterns, the spread of diseases, or the behavior of particles in quantum mechanics, these models are built on assumptions that simplify the real world into manageable equations. While these assumptions can yield remarkably accurate predictions under certain conditions, they are, by necessity, approximations. The reality is that the models themselves are subject to error, and the uncertainties in the initial conditions or the limits of our computational power ensure that absolute certainty remains out of reach. The brilliance of mathematics lies in its ability to reduce complexity to something understandable, yet in doing so, it may obscure the very unpredictability it aims to tame. Mathematics also gives rise to what are known as confidence intervals and other measures of variability, which explicitly acknowledge uncertainty even in the presence of precise numerical estimates. These constructs are designed to capture the range within which the true value of an unknown parameter is likely to fall. Paradoxically, While these intervals illustrate that uncertainty is recognized, the focus on an estimated midpoint or a most likely outcome can still steer our thinking toward a sense of precision that belies the inherent variability of the system. In statistical practice, this duality between the explicit acknowledgement of uncertainty and the compelling clarity of a single number epitomizes the mathematical illusion of certainty. EPR paradox is a foundational concept in quantum mechanics that dramatically challenges our classical understanding of reality by revealing that, at a fundamental level, the fabric of the universe may be intrinsically non-local and interconnected in ways that defy everyday intuition. Formulated in 1935 by Einstein, Podolsky, and Rosen, the paradox arose from an attempt to demonstrate that quantum mechanics, as then understood, implied spooky actions at a distance, meaning that measurements performed on one particle could instantaneously affect the state of another particle, no matter how far apart they are. This phenomenon of quantum entanglement is captured by the mathematics of Hilbert spaces, where each particle is described by a wave function that encodes all possible outcomes. When two particles become entangled, their combined wave function no longer factors into independent parts. Instead, it represents a single, inseparable quantum state that spans both particles. In classical physics, objects are assumed to have their own distinct properties, independent of observation, and any interaction is limited by the speed of light, a cornerstone of relativity. The EPR paradox, however, suggests that if quantum mechanics is complete, then measuring one part of an entangled pair immediately determines the state of the other, an implication that troubled Einstein and his colleagues, because it appeared to violate the principle of locality. They argued that this indicated a gap in quantum theory, proposing instead that hidden variables must exist to account for the observed correlations without resorting to instantaneous effects across space. Mathematically, the situation is described through the formalism of quantum mechanics, where observables such as spin, position, or momentum are represented by operators acting on a wave function in a complex vector space. The intriguing aspect comes from the property of superposition. Before measurement, the particles exist in a state that is a blend of all possible outcomes. Upon measurement, however, the system collapses to a definite state, a process that, despite various interpretations, remains one of the most debated aspects of quantum theory. What is astonishing is that this collapse appears to occur instantaneously across potentially vast distances. The mathematical structure, with its non-commutative operators and probabilistic interpretation via the Born rule, predicts these correlations with remarkable accuracy, even if it challenges our classical notions of causality. This tension between the predictions of quantum mechanics and the classical principle of local causality was later addressed by John Bell in the 1960s. Bell derived inequalities, known as Bell's inequalities, that provide a way to test whether local hidden variable theories, which would preserve a classical sense of separability and cause and effect, could reproduce the statistical correlations predicted by quantum mechanics. Experiments that followed, beginning with those by Alain Aspect and collaborators in the 1980s, consistently showed violations of Bell's inequalities, strongly supporting the quantum mechanical predictions over any local realist interpretation. The violation of these inequalities implies that no theory based solely on local, predetermined variables can explain the observed phenomena, a conclusion that forces us to accept that the universe operates in a way that is fundamentally counterintuitive to our everyday experiences. EPR Paradox is not only a theoretical puzzle, but also a beacon that has illuminated various cutting-edge developments in quantum theory. Its implications stretch into the burgeoning fields of quantum computing and quantum cryptography, where the non-local properties of entangled states are harnessed for tasks that are impossible using classical systems. In these domains, the mathematical principles underlying the paradox translate into practical protocols. Quantum computers exploit entanglement to perform complex computations simultaneously across multiple states, and quantum cryptography uses the properties of entangled particles to achieve secure communication channels immune to eavesdropping. Philosophically, the EPR paradox invites deep reflection on the nature of reality itself. It raises enduring questions. Do particles possess definite properties prior to measurement? Is the act of measurement creating reality rather than merely revealing a pre-existing condition? The mathematics of quantum mechanics, with its elegant yet abstract formalism, forces us to confront these queries. While the theory provides extraordinarily precise predictions, it simultaneously disrupts our intuitive, classical picture of a clockwork universe where every event has a clear, local cause. In summary, EPR Paradox is a profound demonstration of how advanced mathematics can uncover a reality that is more interconnected and, in some ways, stranger than we ever imagined. It shows that the world at the quantum level is governed by principles that defy classical intuition, principles that continue to inspire both technical advancements in quantum technologies and philosophical debates about the true nature of existence. Through its rigorous mathematical formulation and the experimental validations that followed, the EPR paradox has become a cornerstone in understanding quantum non-locality and remains a shining example of how the language of mathematics can reveal the extraordinary depths hidden within the fabric of the universe.